Hello there, and welcome to the Cosmographer. The smallest structure on tonight's list is 9 times wider than the planet you are lying on, and it barely earns its place, because the largest is roughly 1,000,000,000,000 times wider still. Between those two extremes, this countdown climbs through 10 of the largest things ever found in space that science cannot explain. You will meet a pair of jets launched by a single black hole, 23 million light-years from tip to tip, 140 Milky Ways laid end to end. A bubble of galaxies 1 billion light-years wide that appears to be a fossil of the Big Bang's own sound. A cord of matter weighing as much as 200,000 Milky Way galaxies, the heaviest structure ever measured. And a whole 2 billion light-years across that you, and every telescope on Earth, may be living inside right now. As for the structure at the top of this list, it is so large that, if it is real, the universe should not have been able to build it. 10 structures, ranked from smallest to largest, each one bigger than the last. Get comfortable and settle in. If falling asleep to the universe's biggest open questions sounds like your kind of night, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this countdown, you will know why the largest object ever proposed still carries a question mark for a foundation. Now, let's begin at number 10. Number 10. The ghost moons of Earth. Every object on this list is a structure, and every structure on this list is a problem. That is the simple promise of the next 3 hours. We are going to climb a ladder of 10 rungs, and each rung is larger than the one before it. Some of these structures are contested, meaning serious astronomers still argue about whether they exist at all. Some are confirmed beyond reasonable doubt, yet nobody can explain how they formed. And some are so large that their existence, if it holds up, would break one of the founding rules of modern cosmology. That rule is worth stating plainly at the start, because we will return to it again and again. It is called the cosmological principle, and it says that on large enough scales, the universe is supposed to look the same everywhere, and the same in every direction. No special places. No privileged corners. No shapes drawn across the sky. From that single assumption, cosmologists have calculated a rough ceiling on how large any genuine structure should be, and that ceiling sits at about 1.2 billion light-years. Hold that number. More than half the entries on this list either brush against it or crash through it entirely, and the final entry exceeds it by nearly a factor of 10. But a good ladder starts on the lowest rung. And the lowest rung of this countdown is not out among the galaxies at all. It is closer to you tonight than the far side of the moon, and it took 57 years of argument to prove it was real. Our planet, by the official count, has exactly 1 moon. That is the answer every textbook gives, and by the strict definition of a moon, the textbooks are right. But since 1961, astronomers have argued about 2 faint companions that may be traveling with us anyway. They are not solid worlds. They are clouds, immense and nearly invisible, and by the best modern measurements, each one spans roughly 100,000 kilometers by 70,000 kilometers. Line up 9 Earths side by side, and you have the width of one of these clouds. They are called the Kordylewski dust clouds, and for most of the past 6 decades, respectable opinion held that they were probably not there at all. The story begins with a Polish astronomer named Kazimierz Kordylewski, working in Krakow in 1961. Through a telescope, under dark skies, he photographed 2 diffuse patches of brightness, faint smudges that looked almost like thin cloud caught in the starlight. What made the observation remarkable was not the smudges themselves, but where they sat. They appeared suspiciously close to 2 special positions in the Earth and Moon system, positions known as the L4 and L5 Lagrange points. Those points deserve a short explanation, because they are the reason this entire mystery exists. In any system where a small body orbits a large one, the mathematics of gravity produces 5 locations where the pull of the two bodies and the motion of the orbit come into balance. A small object placed at one of these locations can, in principle, stay there, circling in formation with the system instead of drifting away. The French and Italian mathematician Joseph-Louis Lagrange worked this out in 1772 in a paper that won a prize from the Paris Academy of Sciences, and the 5 balance points have carried his name ever since. They are labeled L1 through L5, and they are not all equal. The first 3 lie along the line connecting the two bodies, and they are unstable. An object placed there sits like a marble balanced on the crown of a hill. It can rest for a while, but any small push, from sunlight, from the solar wind, from the tug of another body, will send it rolling off. That is why spacecraft stationed at these points have to work to stay put. The Soho Solar Observatory, parked at the first Lagrange point between Earth and the Sun, and the James Webb Space Telescope, parked at the second, both fire their thrusters on a regular schedule, roughly every 3 weeks, making small corrections to hold their positions. But L4 and L5 are different. Each of them forms an equilateral triangle, with the two large bodies riding 60 degrees ahead of and behind the smaller one in its orbit. These 2 points are stable. An object placed there sits not on a hilltop, but in a shallow bowl. Nudge it, and instead of escaping, it wanders in slow loops around the balance point, held by gravity in a kind of patient orbit around nothing. Nature has run this experiment for us elsewhere in the solar system, and the results are dramatic. At the L4 and L5 points of Jupiter and the Sun, thousands upon thousands of trapped asteroids have accumulated over the ages. We call them the Trojans, and an entire NASA mission, named Lucy, was launched in 2021 to visit them. Where the universe provides a stable parking space, things tend to park. So when Kordylewski reported faint clouds sitting at the stable points of the Earth and Moon system, the claim made a certain physical sense. Dust should gather there. The problem was the evidence. The patches he photographed were desperately faint, fainter than the Gegenschein, which is the dim glow of sunlight scattered back from ordinary interplanetary dust, and that glow is itself one of the most difficult things in the night sky to see. His photographs were taken on glass plates with long exposures, and the images were so weak that newspapers could not even reproduce them. Other astronomers went looking. Some claimed to see the clouds in one point or the other. Most saw nothing at all. And so the argument began. It is worth pausing on how strange this situation was. By the 1960s, astronomy could measure the brightness of stars billions of light-years away. Yet here were 2 objects, each 9 times wider than the planet we stand on, sitting at about the distance of the Moon, and the field could not agree on whether they existed. The clouds were, in the most literal sense, hiding in plain sight. That phrase is worth remembering, because it will return later on this list, attached to something almost unimaginably larger. The 1960s brought the clouds their first taste of official respectability. In 1966 and 1967, NASA organized observing campaigns from its Convair 990, a 4-engine jet converted into a flying laboratory. Cruising at roughly 12 kilometers, far above the haze and light of the ground, observers aboard those flights reported identifying the dust clouds at both the L4 and the L5 points, and even managed to photograph the cloud at L5. Photometric measurements from orbiting observatories in the years that followed added further support. For a moment it seemed the matter might be settled. It was not. In 1976, researchers at the Max Planck Institute for Astronomy ran numerical simulations of the region and concluded that the environment was less friendly than the simple picture suggested. The Sun's gravity, the solar wind, and the pull of the other planets all reach into the Earth and Moon system, and their combined influence, the simulations argued, should disturb the delicate balance at the triangle points enough to prevent dust from settling permanently, particularly at L4. Radar searches of the regions came back empty. Then, in 1983, a careful hunt using a 61-centimeter telescope near Tucson, Arizona, found no trace of a cloud at either point. The skeptics appeared to have the stronger case, and the Kordylewski clouds drifted toward the status of a polite historical embarrassment. And then they came back. In 1989, the Polish astronomer Maciej Winiarski photographed the clouds from an observing station in the Bieszczady Mountains of southern Poland. His were the first 3 color photometric observations ever made of the clouds, and they carried a genuine surprise. The clouds appeared distinctly redder than the Gegenschein. That mattered, because it suggested the dust in the clouds was not simply the ordinary interplanetary dust that fills the inner solar system. Something about its composition or the size of its grains was different. The observation raised a question that remains open to this day. If these clouds are real, where does their dust actually come from? The 1990s added one more negative result to the ledger, and it was an important one. Japan's Hiten spacecraft, a small lunar mission carrying a German-built instrument called the Munich Dust Counter, swung through the regions around both triangle points in 1991 and 1992. It detected no concentration of dust whatsoever. On its face, that sounds decisive. A spacecraft flew through the supposed clouds and felt nothing. But the pass was a single fast loop through each region, a needle drawn once through a haystack, the width of 9 Earths. If the cloud particles were sparse and slow-moving, a lone traverse could easily miss them. The believers were not persuaded to give up, and the skeptics were not persuaded to believe. After 3 decades, the score was still even. The resolution, when it finally came, arrived not from a space agency, but from a garden. Judith Slisz-Baloch, a Hungarian astronomer, operated a small private observatory at Badog-Szony Tordemik, a village near the shore of Lake Balaton in western Hungary. Together with the physicists Gabor Horváth and András Bárta, she went after the L5 cloud with a technique the earlier searchers had never used, imaging polarimetry. The idea is elegant. When sunlight scatters off dust particles, the scattered light becomes partially polarized, meaning its waves pick up a preferred orientation. The angle and strength of that polarization depend on the geometry of the scattering, and a cloud of dust at a Lagrange point should imprint a particular, predictable polarization pattern on the sky, a signature that ordinary skyglow cannot fake. Imagine standing in that garden observatory on a moonless stretch of night. The telescope is aimed at a patch of sky that looks, to your eye, like absolutely nothing, an anonymous darkness 60 degrees behind the moon along its orbit. The camera gathers frame after frame through polarizing filters, each frame a few minutes of accumulated starlight and skyglow and noise. 1 frame shows nothing. 10 frames show nothing. Then the processing begins, the frames are stacked and compared, and slowly a pattern rises out of the randomness. Across the field, the light is arriving with a preferred angle, gentle but consistent, exactly the fingerprint that theory predicts for sunlight scattered by a sheet of dust trapped at the balance point. You are looking at the photograph of a thing that cannot be photographed, drawn not in brightness, but in the orientation of light waves. Somewhere out there, along your line of sight, a cloud that had been doubted for 2 generations is quietly declaring itself. In 2018 and 2019, the team published their results in 2 papers in the monthly notices of the Royal Astronomical Society. The polarization pattern at L5 matched the theoretical prediction for scattering by dust particles, and the authors stated the conclusion directly. The scattered light could not plausibly be anything other than dust. Alongside the observations, they ran a computer simulation that followed the motion of 1,860,000 individual dust particles moving under the gravity of the Earth, the Moon, and the Sun. The simulation showed that particles really can be captured around L5 and held there, and the cloud that formed in the computer matched the shape and the size of the cloud seen from the garden in Hungary. In 2022, the same group extended the work and reported the first polarimetric evidence for the companion cloud at L4 as well. 57 years after Kordylewski's photographs, both of his ghost moons had finally left fingerprints. There is a human weight to this that deserves a moment of quiet. Kazimierz Kordylewski spent much of his career defending two faint smudges that many colleagues regarded as optical illusions, artifacts of wishful looking. He kept observing, kept organizing expeditions, kept arguing, and he died in 1981, 37 years before the confirmation arrived. The vindication, when it came, was not delivered by a flagship space telescope or a billion-dollar mission. It came from a small private observatory in a Hungarian village, from patient people collecting polarized light a few photons at a time. Science does not always move at the speed of its instruments. Sometimes it moves at the speed of someone's stubbornness, and sometimes the person who was right does not live to hear it said. So the clouds are real. Why then do they open a list of structures we cannot explain? Because nearly everything else about them remains unresolved. Start with the disagreements of the past. Why did some careful observers find the clouds while others, equally careful, found nothing? The modern picture suggests an answer that raises new questions. The measurements and the simulations indicate that the clouds are not fixed monuments. Their density appears to shift in rhythm with the Moon's orbital period, and the whole structure may be continuously fed and continuously stripped, losing dust to the pull of the Sun and the pressure of sunlight, then gathering more. One research summary described the picture as an ever-changing dust storm, rather than a stable cloud. The clouds may thicken, thin, disperse and reform, which would explain rather neatly why the history of their observation reads like a decades-long argument between reliable witnesses. Both sides may have been telling the truth about what the sky showed them on the nights they looked. But if the clouds are constantly draining, something must be refilling them, and nobody can yet say what. Micrometeoroid impacts on the Moon throw up dust. The stream of particles that produces meteor showers passes through the system. The zodiacal cloud provides a background supply. Which source dominates, how much mass moves through the clouds, and on what time scale, are all open questions. So is the puzzle of Winiarski's colors. Why should trapped dust be redder than the interplanetary dust around it? Different grain sizes, different origins, different aging under sunlight. Each is possible, none is established. Even the total mass is startlingly uncertain. The particles are thought to be around a micron in size, a millionth of a meter, comparable to a bacterial cell, and they are spread so thinly that the combined mass of a structure 9 Earths wide may be almost trivially small. A cloud can be enormous and nearly empty at the same time, and that combination, immense extent with almost no substance, is precisely what makes it so difficult to pin down. It is a structure at the very edge of what the word structure means. And there is a practical edge to all of this, because the real estate in question is valuable. The stable triangle points of the Earth and Moon system are natural harbors, the best free parking in near-Earth space, and they have long been proposed as sites for relay stations, deep space telescopes, fuel depots, and, in the more ambitious drawings, permanent stations. A spacecraft loitering in a dust cloud, even a sparse one, faces a slow rain of micron-sized impacts, each harmless alone, each sandpapering optics and solar panels over years. Before anyone builds a harbor at L4 or L5, someone will need to finish the survey that Kordylewski started in 1961. The first structure on our list, in other words, is not a distant curiosity. It sits in our own orbital neighborhood, close enough that our satellites fly past it, and it spent 57 years teaching astronomy a lesson in humility. Even the sky directly over our heads still holds things we have not settled. It helps to place the Kordylewski clouds in the family of Earth's other strange companions, because our planet turns out to keep more complicated company than the textbooks suggest. Astronomers have identified a small class of objects called quasi-moons, asteroids that appear, from our vantage point, to circle the Earth in looping paths. Watch one for long enough and the illusion resolves. A quasi-moon is actually orbiting the Sun, on a path so similar to Earth's own that the two bodies travel together for centuries, the asteroid seeming to dance around us while really only keeping pace alongside. Then there are the genuine mini-moons, small asteroids that wander close enough to be truly captured by Earth's gravity for a while. These are rare and fleeting guests. Only a handful have ever been identified, and none remains in orbit today. One of the best documented, a car-sized rock, designated 2020 CD3, was caught by Earth's gravity and circled us as a true second moon from around 2019 until May of 2020, when it slipped back into orbit around the Sun. A temporary moon the size of a car, visiting for about a year, and it still made headlines around the world. Against that family, the Kordylewski clouds stand apart in a remarkable way. Mini-moons come and go within months or years. Quasi-moons keep their formation for centuries. But the gravitational wells at L4 and L5 have existed for as long as the Earth and Moon have existed together, which is over 4 billion years. If dust gathers there today, dust almost certainly gathered there through the deep past as well. The clouds themselves may empty and refill on timescales of months, but the trap that creates them has been set since before life arose on Earth. In that sense, the ghost moons may be simultaneously among the youngest structures in the sky, their particles freshly caught, and among the oldest, their location fixed since the solar system's infancy. There is also a lesson in why these clouds were so punishing to observe, because the difficulty is not incidental. It is the whole character of the object. To see a Kordylewski cloud from the ground, everything must cooperate at once. The sky must be extraordinarily dark, free of moonlight, free of city glow, free of haze. The cloud must be well placed above the horizon, away from the zodiacal light, the glowing band of interplanetary dust that outshines it. And the observer must be able to distinguish a patch of sky that is perhaps a few percent brighter than the blackness beside it, a contrast so slight that the human eye, and most instruments, simply average it away. The astronomers who succeeded, from Kordylewski onward, were specialists in exactly this kind of threshold seeing, and the ones who failed were often equally skilled, working on nights when the clouds may genuinely have thinned to nothing. Very few objects in astronomy punish their observers this way, sitting forever at the boundary between detection and doubt. It is fitting that the technique which finally settled the question, polarimetry, does not ask how bright the sky is at all. It asks how orderly the light is, and order, unlike brightness, cannot be faked by a fluctuating atmosphere. Hold on to the width of that lesson, 9 Earths side by side, because it is the first rung of the ladder, and the ladder now climbs steeply. From 2 clouds our own cameras could barely find, the countdown jumps to a single object so long that 140 galaxies the size of our own could be laid end to end inside it, and all of it was launched by one black hole. Number 9. Porphyrion, the longest jets ever seen. In September of 2024, the journal Nature put a radio image on its cover, that forced astronomers to redraw the upper limit of what a single object can do. The image showed a pair of jets, two beams of plasma erupting from a single point and racing in opposite directions, and the distance from the tip of one jet to the tip of the other measured 23 million light-years. That number deserves context, because numbers this large slide off the mind unless we anchor them. Our Milky Way galaxy, with its hundreds of billions of stars, is about 100,000 light-years across, and crossing it at the speed of light would take 1,000 human centuries. The structure in that radio image is 140 Milky Ways long. It is roughly 10 times the distance between our galaxy and Andromeda, our nearest large neighbor. If you scaled the Earth down to a single grain of sand, the Kordylewski clouds from our last entry would be a smudge a few centimeters wide sitting beside it. On that same scale, this object would still be too large to fit inside the orbit of the Moon. And the entire thing, every light-year of it, was produced by one supermassive black hole. The Discovery team named it Porphyrion, after a giant from Greek mythology, one of the monstrous children of the Earth goddess Gaia, who made war on the gods of Olympus. The name was chosen with care, and it continued a small tradition. A few years earlier, essentially the same team had found the previous record holder, a jet system 16 million light-years long, and named it Alcyoneus, after Porphyrion's brother. The giants of mythology were beings too large for the ordinary world to contain, and that is a fair description of what these objects are to astrophysics. The instrument behind the discovery is called LOFAR, the Low Frequency Array, and it is one of the strangest telescopes ever built. It has no great mirror and no dish. It is a network of many thousands of simple radio antennas, spread in stations across the Netherlands and half a dozen other European countries, all wired together so that a continent effectively behaves as a single enormous radio eye. LOFAR listens at very low radio frequencies, the part of the spectrum where the oldest and faintest plasma in the universe still whispers, and that makes it ideally suited to finding the outer reaches of giant jets, the dilute lobes that other telescopes miss. Beginning in the early 2020s, a team led by the astronomer Martijn Ooi, working between Leiden Observatory in the Netherlands and Caltech in California, began systematically sweeping LOFAR's sky maps for these giants. They expected to find some. What they found instead was a population. More than 10,000 giant jet systems surfaced in the survey, an order of magnitude beyond what anyone had catalogued before, and the record breaker among them was Porphyrion. Confirming it took a chain of telescopes across the world. The giant Metrowave radio telescope in India verified the radio structure. The Keck Observatory in Hawaii and the Mayol telescope in Arizona, running the DESI instrument, identified and measured the galaxy from which the jets erupt. The verdict placed the source 7.5 billion light-years away, which means the light in that nature cover image left home before the Earth existed, when the universe was less than half its current age. The host is a heavyweight, a galaxy roughly 10 times the mass of the Milky Way, and at its heart sits the engine, a black hole with a mass of hundreds of millions of suns. It is worth taking a moment on how an engine like that works, because the mechanism is one of the most efficient in nature. A supermassive black hole does not simply swallow what falls toward it. Infalling gas spirals inward through a flattened disk, growing hotter and faster as it descends, and the disk becomes threaded with magnetic fields, twisted and wound by the spin of the whole system. Under the right conditions, those fields organize into a pair of channels above the black hole's poles, and a fraction of the inflowing matter is caught, accelerated to nearly the speed of light, and flung outward along the spin axis in two opposed beams. The result is a natural particle accelerator, powered by gravity, and at full output, it can outshine every star in its host galaxy combined. The total power carried by Porphyrion's jets has been estimated at the output of trillions of suns. A single structure, launched from a region smaller than our solar system, carrying the energy budget of 10,000 galaxies worth of starlight, sustained for an age of the universe. Now come the problems, and they are serious enough that Porphyrion earns its place on this list of things we cannot explain. The first problem is stability. To grow 23 million light-years long, a jet must remain narrow, straight, and continuously powered for an extraordinarily long time. The team's estimates suggest the black hole must have fired steadily for on the order of 1 billion years. Think about what that requires. The gas supply feeding the black hole cannot sputter. The spin axis cannot wander, or the jets would carve spirals and cones instead of clean lines. And the beams themselves must hold together across intergalactic distances. Physics knows many ways for a beam of plasma to fail. Fluid instabilities can make it kink and buckle like a garden hose under too much pressure. Interaction with the gas it plows through can shred its edges. Long before the 2024 discovery, theorists generally expected such instabilities to disrupt jets well before they reached this scale. Porphyrion simply ignores that expectation. The most useful comparison is a thread of smoke rising from a candle. For a few centimeters, the thread rises straight and smooth, and then, inevitably, it wavers and dissolves into curls. Every intuition we have about flowing matter says that order on that scale decays quickly. Porphyrion is a thread of smoke that stayed straight for 140 galaxies, and nobody can fully say why. Picture riding it. You are a passenger on a beam of light, surfing along the jet from its engine outward, moving at the fastest speed the universe allows. Beneath you, the column of plasma glows in radio light, narrower than a galaxy, rushing in a straight line through the dark. Entire galaxies drift past in the distance like harbor lights seen from a ship at sea, first one, then a cluster of them, then more, each one a city of billions of stars, each one left behind. You ride for 1,000 years, and the beam does not bend. You ride for 1,000,000 years, and the beam does not bend. The journey from the black hole to the jet's tip, at the speed of light, lasts 23 million years, and when you finally arrive at the end, where the plasma billows out into a lobe like smoke against glass, the galaxy that launched you is no longer visible behind you. It is somewhere back in the dark, 23 million light-years away, still firing. The second problem is the engine's personality. Astronomers know supermassive black holes operate in two broad modes. In one, sometimes called the radiative mode, the black hole feeds richly from a bright disk, blazing as a quasar, pouring out light. In the other, the jet mode, the feeding is leaner, and the output comes primarily as beams of plasma rather than radiation. The general expectation was that the longest jets in the universe would come from the second kind, the lean, jet-focused engines. But when the team examined Porphyrion's host, they found the signature of the first kind, a radiative, quasar-like engine, the type not expected to hold the long jet record. The largest jet structure ever seen is being driven by the wrong sort of engine. That is not a detail. It suggests that our categories for how black holes convert matter into power are incomplete, and that the radiative engines scattered through the young universe, which were common, may have been quietly capable of feats we never assigned them. And that leads to the third problem, which is the largest of all. Porphyrion is not just a curiosity. It is a messenger from an era when the universe was denser and busier, and it implies that jets of this scale may have been reaching out of galaxies when the cosmic web, the great network of filaments and voids that matter organizes itself into, was still young. A jet 23 million light-years long does not stay inside its own galactic neighborhood. It reaches out of its galaxy, out of its group, and into the web itself, into the thin gas between galaxies. Along the way, it deposits energy, fast particles, and, crucially, magnetic fields. One of the standing puzzles of cosmology is why magnetism seems to thread even the emptiest reaches of space, and giants like Porphyrion offer a possible answer. If the young universe was full of such engines, they may have seeded the web with magnetism, the way a few industrial cities can smoke up an entire sky. Whether that story is true, and how much of the universe's hidden magnetism was planted by black holes, is unresolved. The 23 million light-year giant is evidence that the reach of a single black hole extends much farther than anyone had licensed it to. Here is the human scale of the matter. Our own galaxy sits inside the same cosmic web that these jets reach into, and the space the Milky Way swims through may carry old fingerprints of engines like this one, magnetism laid down billions of years ago by giants that have long since gone quiet. When you look at the night sky, you are looking through an environment that may have been engineered, in part, by black holes acting at distances we only just learned were possible. The record books were rewritten by a single radio image, and the survey that produced it has thousands of giants still waiting for close study. Nobody believes Porphyrion will hold the record forever. To appreciate how thoroughly Porphyrion rewrote the record book, it helps to know the family it belongs to, because giant radio jets have a distinguished history. Astronomers have known since the 1950s that some galaxies pour out radio waves from enormous twin lobes, plasma balloons inflated on either side of the visible galaxy. The classic example, a galaxy called Cygnus A, is one of the brightest radio sources in the sky, its jets feeding lobes that span a few 100,000 light-years, a few times the width of the galaxy itself. That was the standard picture for decades, jets somewhat larger than their hosts. Then came the class known as giant radio galaxies, systems whose lobes stretch across millions of light-years, and the record crept upward, one discovery at a time, 3 million, 5 million, 10 million. When Alcyoneus was announced in 2022, at 16 million light-years, it seemed a ceiling had surely been reached, and the astronomers who found it said as much, wondering in print what could possibly allow a jet to grow larger. 2 years later, their own survey answered with Porphyrion, 40% longer still. The record has now been broken so many times, by such widening margins, that the researchers involved have largely stopped speaking of ceilings. The honest position is that nobody knows how long a black hole's reach can be, and the sky has not finished correcting us. It is also worth asking what such an object would mean if it were near us, because distance sanitizes these numbers. There is, helpfully, a preview hanging in Earth's southern sky. The nearest actively jetted giant galaxy, Centaurus A, lies a mere 12 million light-years away, and its radio lobes, though vastly smaller than Porphyrion's, are close enough that they span a portion of our sky 20 times wider than the full moon. If human eyes could see radio light, Centaurus A would be one of the largest single objects in our heavens, a double plume rising from a point of light, and every culture in the southern hemisphere would have myths about it. Now perform the substitution. Place Porphyrion's engine where Centaurus A sits, and its jets would not decorate a region of our sky. They would cross the entire sky and keep going, a structure passing our galaxy the way a transcontinental cable passes a farmhouse, its two ends farther away than every galaxy an amateur telescope can show you. The exercise is fanciful, but it makes the essential point. Objects of this class are not larger versions of things we know. They belong to a different category of presence, single machines operating on the scale where the universe's own architecture is the only fair comparison, and the sky we happen to have, with no such giant nearby, is a quiet sky by cosmic standards. The radio surveys are teaching us how many louder skies exist. There is also the question of how one measures the age of a thing like this, and the answer is written in the plasma itself. The particles in a jet broadcast radio waves because they are spiraling through magnetic fields at nearly the speed of light, and as they broadcast, they spend their energy. Fresh plasma, recently accelerated, shines brightly at higher frequencies. Old plasma, coasting for millions of years, fades toward the low frequencies where only instruments like LOFAR can hear it. Reading the spectrum of a jet from its engine out to its distant tips is therefore like reading tree rings, a record of energy spent across time, and it is this kind of reading, combined with the sheer light travel time along the structure, that tells astronomers Porphyrion's engine must have burned steadily on the order of 1 billion years. 1 billion years of steady output from a single machine the size of a solar system. For comparison, in 1 billion years our Sun will have brightened enough to begin sterilizing the Earth. Entire chapters of planetary history fit inside the operating log of this one engine. And the environment matters as much as the engine. Porphyrion lived in the young universe, when everything was closer together and the cosmic web was tighter, its filaments thinner and its voids smaller than today. A jet 23 million light-years long in that era did not merely leave its galaxy. It crossed its own filament and reached into the voids beyond, which means the energy it carried was delivered not to its neighborhood, but to the general fabric of the cosmos. Astronomers calculate that jets are among the most efficient long-distance delivery systems the universe possesses, moving energy from the densest environments, galactic cores, to the emptiest ones, the deep web, in a single connected structure. If even a modest fraction of early black holes drove jets on this scale, then the temperature, the magnetism, and the cosmic ray content of the spaces between galaxies were partly set by them, and some of the properties of today's universe that we attribute to primordial physics may instead be industrial residue, the accumulated exhaust of giants. Settling that question requires knowing how many Porphyrions there were, and that census has only just begun. The LOFAR survey covered a fraction of the sky. The team's own estimate is that thousands more giants await in the unexamined data, and the next generation of radio arrays will hear fainter and farther still. But the next entry on this list is not an object at all. It is an absence, a place where the universe forgot to put things, and it begins almost at our doorstep. It is so large and so empty that it is actively pushing our galaxy across the sky. Number 8. The local void, the emptiness next door. Astronomy is usually the study of things. Stars, planets, galaxies, clouds of gas, all the furniture of the universe. But some of the most important discoveries of the past half-century have been the study of nothing, of the places where the furniture is missing. The universe, mapped on the largest scales, is not a smooth fog of galaxies. It is a foam. Galaxies gather along walls and filaments, the filaments knot together into clusters, and between them lie the voids, enormous rounded hollows where hardly anything shines. This structure is called the cosmic web, and our own galaxy is a strand in it. What far fewer people know is that the Milky Way sits directly on the shore of one of these hollows. It begins where our local group of galaxies ends, about 3 million light-years from where you are lying tonight, and it stretches away for at least 150 million light-years, possibly much farther. Astronomers call it, plainly, the local void. It covers roughly 40% of the sky as seen from Earth. And here is the textbook rule to keep beside that fact, the rule this entire list is quietly stress testing. On large scales, the universe is supposed to look the same in every direction. From our shoreline, in one direction there are galaxies beyond counting. In the other direction, for a distance 1,000 times the width of our galaxy, there is very nearly nothing. The local void was first recognized in 1987 by 2 astronomers assembling a map. Brent Tully and Richard Fisher were compiling their Nearby Galaxies Atlas, one of the first serious attempts to chart the three-dimensional layout of our cosmic neighborhood, plotting the positions of thousands of galaxies around the Milky Way. As the atlas took shape, a region of the map insisted on staying blank. Toward the constellations of Aquila and Hercules, beginning just beyond the local group, the catalogue simply ran out of entries. It was not that the galaxies there were too faint or too far. There were no galaxies to record. Tully and Fisher drew the boundary of the blankness as best they could and gave it its modest name, and for the next 3 decades, the local void remained one of the least explored features of the nearby universe, for a frustrating reason. From our position, much of it lies behind the disk of the Milky Way itself, behind the dust and the crowded starfields of our own galaxy, in the band of sky astronomers only half-jokingly call the zone of avoidance. The nearest great emptiness in the universe is partially hidden from us by the very galaxy we live in. To map what you cannot see, you need a trick, and the trick that finally worked is one of the most elegant in modern astronomy. You map the invisible by watching how it moves the visible. Every galaxy in the universe is carried along by the general expansion of space, but each one also has its own private drift, called a peculiar velocity, produced by the gravity of everything around it. Matter pulls. Emptiness, in effect, repels, not because a void pushes on anything, but because a galaxy on the edge of a void is pulled by the crowded side and not by the empty side, and so it drifts away from the emptiness. Measure the drifts of enough galaxies, and the flow lines trace out the hidden landscape of mass, including matter that shines and matter that does not. It is like mapping the bottom of a dark lake by carefully watching the currents on its surface. In 2019, Tully and his colleagues did exactly this, on a grand scale. Their tool was a compendium called Cosmic Flows 3, a painstakingly assembled catalogue of distances and motions for 18,000 galaxies, and from it they constructed the first detailed three-dimensional map of the local void's boundaries, published in the Astrophysical Journal. The picture that emerged was of a truly enormous hollow pressing directly against our cosmic neighborhood, its walls traced by the flows of galaxies streaming away from it, its interior profoundly empty, and its far side still uncertain because the map, once again, runs out where our galaxy blocks the view. Some reconstructions suggest the local void may connect through hidden channels to neighboring hollows, forming a single cavity considerably larger than the mapped portion. Its true size remains an open question. What is not in question is that it is there, that it is expanding in place as voids do, and that it is shoving us. That shove is measurable, and it is not small. Here is how we know. The cosmic microwave background, the faint afterglow of the early universe, fills the sky from every direction and provides an absolute reference frame for motion. Measured against it, the Milky Way, Andromeda, and their entourage of smaller galaxies are traveling at more than 600 kilometers per second in a particular direction, a speed that would cross the continental United States in about 7 seconds. That number has been known for decades, and explaining it, accounting for exactly which masses produce this motion, has been a running project of cosmology for just as long. The 2019 mapping delivered a substantial piece of the answer. Roughly half of that 600 km per second motion, it turns out, is generated locally, by just 2 influences. One is the pull of the Virgo cluster, the nearest great city of galaxies, about 50 million light-years away, whose thousands of members drag us gently toward them. The other is the push of the local void. As the void empties, its former contents draining onto the walls around it, everything on its shoreline is carried outward, and the Milky Way is on that shoreline. The void's contribution alone comes to somewhere between 200 and 260 kilometers per second. Sit with that for a moment. As you lie still tonight, your galaxy, your sun, your house, and you are being moved through the universe at roughly 250,000 kilometers every second, and a substantial share of that motion is caused by nothing at all, by a region distinguished only by what it lacks. We are, in the most literal sense available to physics, running away from an emptiness. So the local void is real, mapped, and dynamically important. Why does it belong on a list of structures we cannot explain? Because of what is missing inside it, beyond even what the name promises. When cosmologists simulate the growth of structure in the universe, beginning from the almost perfectly smooth conditions of the Big Bang and letting gravity work for nearly 14 billion years, the simulations produce voids in abundance, and the voids are never perfectly empty. The same models that fill the walls and filaments with bright galaxies predict that void interiors should retain a thin scattering of small, faint dwarf galaxies, stragglers that formed from the sparse material left behind. The prediction is not marginal. Straightforward accounting suggests the local void's interior should hold something on the order of tens of small galaxies, enough that our surveys, which are quite capable of finding faint dwarfs at these distances, ought to see them. They do not. The void's interior is far cleaner than theory says it should be, nearly swept, and the handful of galaxies that do sit within or near it appear to be evacuating, moving outward at high speeds, as if the emptiness were actively finishing the job. This discrepancy has a name in the scientific literature. It is called the void phenomenon, and it was pointed out as a serious challenge more than 2 decades ago by the cosmologist Jim Peebles, who would later share the Nobel Prize in Physics. It remains unresolved. Either something about how small galaxies form suppresses them in void environments far more efficiently than our models capture, or something about the voids themselves, their depth, their dynamics, perhaps their dark matter content, is different from what we assume. The emptiness next door is not just empty. It is too empty, and nobody knows why. There is one more layer of strangeness. Because the local void presses so close, its influence is woven into measurements we make of everything else. The push it gives us is part of the motion astronomers must subtract when they measure the expansion of the universe from nearby galaxies. Our viewpoint is not a neutral platform drifting in calm water. It is a raft on a current, being carried by the gravity of structures we can only partially see, away from a hollow we have only partially mapped. Every precise claim we make about the universe passes first through a correction for where we happen to stand, and where we happen to stand is on the rim of an anomaly 150 million light-years wide. Part of the direction and speed of everything you have ever seen, every star in every constellation, is set by a hole in the universe next door. The discovery of cosmic voids in general is younger than many people assume, and the story explains why the local void could hide so long. Into the 1970s, most astronomers pictured galaxies as scattered through space more or less evenly, like dust motes in a sunbeam. The first true maps said otherwise. When teams at the Harvard-Smithsonian Center for Astrophysics began systematically measuring galaxy distances in the late 1970s and 1980s, plotting thin slices of the universe in depth, the resulting diagrams became famous almost overnight. The galaxies did not scatter. They gathered into arcs and chains surrounding great rounded blanks, and one celebrated slice appeared to show a stick figure of a human being drawn in galaxies, with empty bubbles for its body. The universe, the maps declared, is built like foam, and the blanks, the voids, are not gaps in our knowledge, but genuine, physical, enormous rooms of near nothing. Voids typically span tens to hundreds of millions of light-years, and they fill, by volume, the majority of the universe. The shining web that contains every galaxy you have ever seen a photograph of is, by volume, the minority. Most of everything is emptiness, and the emptiness is organized. What makes the local void personal is simply that it is ours, and being ours, It is the one void we can study from its own shoreline. That has produced some intimate discoveries. Astronomers have identified a small number of galaxies that live genuinely inside it, isolated in a way almost nothing else in the universe is. One of them, a dwarf galaxy catalogued as KK-246, drifts in the void's interior with no significant neighbor for millions of light-years in any direction. Consider existence in such a place. From a planet inside that galaxy, the night sky would show its own galaxy's stars, and beyond them almost nothing an unaided eye could catch. No bright neighboring galaxies, no crowded cluster sky, just darkness of a purity our own sky never reaches. An astronomer evolving there might reasonably conclude the universe consisted of one galaxy alone, and might build cosmology on that mistake for centuries. Our own situation differs from theirs only in degree. We too draw conclusions about everything from inside a particular somewhere, which is a thought this list will sharpen considerably before the night is over. The void's push also connects to one of the oldest puzzles of local astronomy, the question of where our galaxy is going. Since the 1970s, astronomers have known the Milky Way is falling toward the Virgo cluster, while simultaneously moving with a larger flow toward more distant concentrations of mass, and mapping the sources of this motion, assigning responsibility for each portion of our 600 km/s drift, has taken half a century of labor. The 2019 result, crediting a fifth or more of the entire motion to the local void's expansion, was in some ways the most surprising entry in that ledger, because it assigned a leading role to a region containing, by cosmic standards, nothing. Gravity's arithmetic does not care. A deficit of matter on one side moves you exactly as effectively as a surplus on the other, and the deficit beside us happens to be one of the largest mapped. When astronomers finally chart the void's far side, hidden today behind our own galaxy's disk, the arithmetic will be completed, and we will know for the first time the full shape of the emptiness that has been steering us since before there was an us. The push itself deserves one more moment because the mechanism rewards clear picturing. It might seem mystical that emptiness can move a galaxy, so consider the situation from the Milky Way's point of view. Our galaxy hangs in space, surrounded on all sides by matter whose gravity tugs at us, a tug from every direction at once. If the surroundings were perfectly even, every tug would cancel, and we would drift with the pure expansion of the universe, motionless in the local sense. But our surroundings are not even. On one side, toward Virgo and beyond, the universe is crowded, walls and clusters pulling with their combined weight. On the opposite side lies the local void, and from that whole quarter of the sky, the answering pull barely comes. The imbalance does the moving. We accelerate toward the crowded side, year after year, and the bookkeeping of physics permits two equally true descriptions, that the far structures pull us, or that the void pushes us. Astronomers use the second phrasing freely, and even speak of voids exerting an effective repulsion, because in the mathematics of the flow maps, an underdense region behaves exactly like a region of negative mass, a hill in the gravitational landscape down which everything nearby rolls away. It is a strange inversion of intuition. In the universe's terrain, matter digs valleys and emptiness raises hills, and our galaxy is partway down a long slope with a hill of nothing at our backs, gathering speed. Run that arrangement forward, and the void's future writes itself. Emptiness that repels grows emptier, and growing emptier repels more strongly. Over the coming billions of years, the local void will continue evacuating, its remaining stray galaxies fleeing to its walls, its volume swelling as the universe's accelerating expansion assists the process, and the contrast between the crowded web and the hollow rooms will deepen without limit. Astronomers describe the far future of the cosmos as a landscape of ever richer walls around ever purer voids, structure sharpening even as it spreads apart. In that long view, the local void is not a static feature of our neighborhood. It is an active process happening beside us, a slow explosion of nothing, and the 250 kilometers per second it has already given the Milky Way is simply the speed the process has reached in our era. The number will grow. It is a strange thought to keep beside the evening's calm. The stillest thing in the sky, a region defined by absence, is the most persistent worker in our corner of the universe, and it never rests. And keep that textbook rule in mind, the universe looking the same in every direction because the strain on it has only begun. If an absence this large can push a galaxy, the next entry on the list shows what the opposite looks like, matter gathered rather than missing, and gathered into something almost impossible to picture. It is a shell of thousands of galaxies, a full billion light-years across, and it appears to be the fossil of a single sound wave that has been frozen since the universe was 380,000 years old. Number 7. Hercules-Corona, the billion light-year bubble. Some discoveries are hunted for decades. Others are tripped over. The 7th entry on our countdown belongs firmly to the second kind, because the astronomers who found it were not looking for it, did not expect it, and at first could hardly believe the size of what their own map was showing them. In September of 2023, a team led by Brent Tully, the same Brent Tully who co-discovered the local void of our last entry, announced in the Astrophysical Journal the identification of a single coherent shell of galaxies, approximately 1 billion light-years in diameter. Its center lies about 820 million light-years from us, which by the standards of this list counts as the nearby universe. It was given the name Hercules-Corona, drawn from the Kumulipo, the great Hawaiian creation chant, a word evoking scent murmurs of awakening. The name was suggested by Nawa Napoleon, an expert in Hawaiian language, and it honors the discovery's home institution, the University of Hawaii's Institute for Astronomy. But the most remarkable thing about Hercules-Corona is not its size, though the size alone would earn its place here. It is what the structure appears to be. Hercules-Corona seems to be a fossil, the preserved remains of a single sound wave that rang through the universe in its first 380,000 years and has been frozen ever since. If that interpretation is right, we are looking at one note of the Big Bang, caught and held for 13.8 billion years, with galaxies strung along its crest like frost on a window pane. To understand what that means, we need to go back to the very beginning, because the physics involved is among the most beautiful ever worked out. In its infancy, the universe was not the black and silent place we know. It was a hot, glowing plasma, a dense fog of hydrogen and helium nuclei, electrons and light, all bound together, filling all of space. Within this fog, gravity and pressure fought a running battle. Wherever matter was slightly denser than average, gravity pulled surrounding material inward. But the plasma was springy. Light itself pushed back, and the compressed regions rebounded, sending pressure waves rippling outward through the fog. These were, in the most physically honest sense of the word, sound waves, oscillations of compression and rarefaction, traveling through the medium of the early universe at over half the speed of light. Every initial clump of matter launched its own expanding spherical wave, ring after ring, like raindrops striking a pond, except the pond was the entire universe, and the ripples were made of matter and light. Then, 380,000 years after the beginning, the music stopped. The universe cooled enough for electrons to settle into atoms, the fog cleared, and light streamed free, becoming the cosmic microwave background we still detect today. With the light no longer coupled to the matter, the pressure that drove the waves vanished, and every ripple simply stopped where it was, mid-stride. Each initial clump was now surrounded by a faint spherical shell of slightly enhanced density, frozen at the distance its sound wave had managed to travel. Over the following billions of years, gravity slowly amplified this pattern. Galaxies formed preferentially where matter was denser, which means they formed at the centers of these fossil patterns and, faintly, along the frozen shells. Astronomers call these fossils baryon acoustic oscillations, and one of the field's genuine triumphs is that they were predicted before they were found. The prediction even specified the size. Given how fast sound traveled and how long it had to travel, every frozen shell should have started at a standard radius, close to 500 million light-years across in today's stretched universe, and surveys of millions of galaxies confirmed the pattern statistically. Buried in the arrangement of galaxies across the sky, there is a preferred separation, a standard interval, exactly as predicted. This standard size is one of cosmology's most trusted rulers. By observing how large the frozen shells appear at different distances, astronomers measure how much the universe has expanded, and the ruler is a cornerstone of the standard model of cosmology. But all of that was statistics, a pattern teased out of millions of galaxies averaged together. No one had ever pointed at the sky and identified one individual fossil shell, a single specific bubble with a name. That is what Tully and his colleagues believe they found. They were working with Cosmic Flows 4, the latest edition of the Galaxy Distance Catalogue we met in the previous entry, mapping the arrangement and motion of tens of thousands of galaxies in the nearby universe. Cullen Howlett of the University of Queensland in Australia, an expert in exactly this kind of statistical structure, examined a suspicious arc of galaxies in the maps, and the analysis kept returning the same answer. The arc was one visible section of a full three-dimensional shell, a sphere of enhanced galaxy density 1 billion light-years wide. The structure was so large that it spilled beyond the boundaries of the sector of sky the team had set out to analyze. They had to widen the map to hold it. And when they looked at what the shell contained, a quiet astonishment set in, because the shell was already covered in famous landmarks. Near its center sits the Bootes supercluster, and around its rim, like beads on a ring, lie structures that astronomers had discovered separately over 4 decades and had always treated as independent monuments. The Sloan Great Wall, one of the largest galaxy walls ever mapped, is part of it. The Hercules superclusters are part of it. Even the CFA2 Great Wall, the chain of galaxies whose discovery in the 1980s first stunned astronomers with the realization that the universe builds on such scales at all, sits within this pattern. It was as if a family had spent 40 years photographing individual peaks, and someone finally climbed high enough to see that all of them were ridges of one single mountain. Ho'olelana, if the interpretation holds, is not a new object, so much as a new reading of the sky we thought we knew. 4 decades of separate discoveries reassembled into one enormous fossil. Picture it from the inside, because there is a vantage point that makes this structure what it is. Imagine floating at the very center of Ho'olelana, at the position of that ancient initial clump of matter. You hang in darkness, and around you, in every direction you turn, at a distance of 500 million light-years, there is a faint thickening of galaxies, a mist of lights arranged on a closed shell that surrounds you completely. It does not glitter or glow as a wall. It is subtle, a statistical breath of extra galaxies, but it is everywhere, above you, below you, on every side, one continuous sphere. You are standing inside a sound. The shell around you is the crest of a pressure wave that stopped moving when the universe was 380,000 years old, and everything it has done since is simply drift apart with the general expansion, its shape preserved, its motion long finished. The galaxies strung along it are younger than the wave they decorate. The wave existed before there were stars to shine on it. You are hearing the early universe in the only way it can still be heard, with your eyes, reading a note of the Big Bang that was sustained for 1/3 of a million years and has been held in silence ever since. The moment the pattern was recognized deserves its own telling, because it captures something true about how discovery actually feels. The analysis was led on the statistical side by Cullen Howlett, whose specialty is exactly the kind of subtle spatial patterning that acoustic fossils imprint, and the algorithms he applied were designed to answer a narrow question: whether the arrangement of galaxies in the cosmic flows maps was consistent with the expected faint shell statistics. When the procedure locked onto the actual shell, center, radius, and density profile, emerging together from tens of thousands of galaxy positions, the result was so clean that the first response was not celebration but wariness. Structures that obvious are usually artifacts. Tully has described his own reaction as astonishment layered over decades of familiarity, because he had spent his career mapping precisely this volume of the universe, naming its walls and streams, and the idea that one enormous coherent pattern had been sitting across all of it, unrecognized, containing his own life's landmarks as ornaments on its shell, was almost an affront. The team tested the arrangement against randomized versions of the same catalog, universes shuffled to erase real patterns while keeping their general texture, and the shuffled skies produced nothing comparable. The shell stayed. It was the kind of result, the discoverers admitted, that they would have been skeptical of in someone else's paper, which may be the most honest compliment nature can pay a scientist. It helps, too, to picture the moment the pattern froze, because the freezing is the whole reason anything survives to be found. For 380,000 years, the young universe glowed, a fog of plasma everywhere the color of a furnace, and the sound waves of our story moved through it as actual traveling compressions, ripples in a medium that filled all of existence. Then, over a stretch of mere tens of thousands of years, cosmically an instant, the fog condensed. Electrons found their nuclei, atoms formed, and the universe went from opaque orange everywhere to transparent black everywhere, the great clearing whose released light still fills the sky as the microwave background. For the sound waves, the clearing was the end of the road. Their medium's springiness vanished mid-oscillation, and each wave halted where the moment caught it, its energy stranded, its pattern bequeathed to the matter it had been carrying. Ho'olelana, on this account, is one such stranded wave, its shell the exact distance sound had managed to travel in the age of the fog. The number that sets its size is, in the deepest sense, the duration of the universe's first era multiplied by the speed of its first sound. When we measure the bubble, we are measuring how long the beginning lasted. So why does Ho'olelana, beautiful as it is, belong on a list of structures we cannot explain? For a reason that cuts directly at the foundations of precision cosmology. It is the wrong size. The whole power of baryon acoustic oscillations comes from their predictability. The frozen shells are supposed to be standard, all sharing the same intrinsic scale, which is precisely what makes them a trustworthy ruler. Ho'olelana is measurably larger than the standard prediction for a shell at its distance. Not enormously larger, but larger by more than the uncertainties comfortably allow. Taken at face value, a fossil shell that appears too big means the space containing it has stretched more than expected, which is to say, the universe in our region has been expanding faster than the consensus rate. When the team followed that logic and derived an expansion rate from Ho'olelana itself, the answer came out high, close to 77 kilometers per second per megaparsec, noticeably above the value of about 67 derived from the cosmic microwave background. That lands this gentle bubble squarely in the middle of the sharpest dispute in modern cosmology, the Hubble tension, the stubborn disagreement between how fast the universe seems to be expanding when measured nearby, and how fast it should be expanding according to the early universe. We will meet that dispute again, 3 entries from now, in a much darker form. For now, the point is simple. Our neighborhood's fossil ruler reads wrong, and either the reading is a fluke or the ruler is telling us something the standard model has not absorbed. There is also a planar possibility, which the discoverers themselves acknowledge with complete honesty. Huge-LQG might not be a true individual baryon acoustic oscillation at all. The universe's foam of walls and voids is complicated, and it is conceivable that several unrelated structures have arranged themselves, by coincidence, into something shell-shaped, a fossil impersonator. The statistical case for the shell is strong but not overwhelming, and the question will only be settled by the next generation of galaxy surveys, which will map this volume of space far more completely. Until then, Huge-LQG remains exactly what this list is for, an enormous, coherent, arguably impossible thing, sitting in our own cosmic backyard, at once the most ancient structure ever tentatively identified and a measurement that quietly disagrees with the universe's official biography. The same frozen music that cosmologists use to measure the age and fate of everything is playing slightly out of tune in our neighborhood, and whether the fault lies in the bubble or in our theories is precisely the open question. It is worth lingering on how the baryon acoustic pattern was first caught, because the detection is one of the great quiet triumphs of modern science, and it explains why astronomers trust the ruler that Huge-LQG now calls into question. The prediction came first, decades before the technology. Theorists working out the physics of the early plasma calculated that the frozen sound pattern must exist and must appear in two places, first as a faint preferred spot size in the temperature speckles of the cosmic microwave background, and second as a faint preferred separation between galaxies, a distance at which pairs of galaxies would be very slightly more common than at distances just smaller or larger. The predicted signal in the galaxies was tiny, a correlation excess of around 1%, meaning no human eye scanning a galaxy map would ever notice it. Finding it required counting on an industrial scale. Through the 2000s, two great surveys, one in Australia measuring 250,000 galaxies and the Sloan survey in New Mexico measuring far more, accumulated enough distances that the statistics could speak. In 2005, both teams announced the bump was there, at the predicted separation, at the predicted strength. The sound of the infant universe had been recovered from the arrangement of galaxies 9 billion years after it stopped playing. It stands among the most stringent confirmations the Big Bang framework has ever received, and from that day forward, the acoustic scale became a workhorse. Survey after survey has measured the bump at different cosmic epochs, watching the frozen ruler stretch with the expansion of space, using it to chart the influence of dark energy itself. Millions of galaxies, decades of labor, all resting on the reliability of one standardized fossil. That history is exactly what makes an individual, nameable, apparently oversized specimen so provocative. The statistical bump is an average over the whole population of frozen waves, all overlapping, each too faint to see alone. Tully, Howlett, and Porphyrion propose that Huge-LQG is one member of that population caught individually, the way a single fossil shell might weather out of a hillside whose strata had only ever been studied in bulk. Averages are robust but anonymous. An individual can be examined, and this individual measures large. The team's analysis fit the shell's profile carefully, modeling where its center should be and how sharply its crest should rise, and the fit kept returning a radius exceeding the standard expectation. They noted, too, that the region at the shell's center is exactly what the theory orders, a concentration of matter that would have been the wave's original source, with the great booty's structures sitting there like the stone that made the splash. The picture is internally consistent in a way a coincidence has no obligation to be. And still, the size discrepancy stands, either a 1 in some odds fluctuation of a single specimen, which is entirely possible and which only more specimens can judge, or the first hint that the trusted ruler reads differently here than the global average, which would be a finding of the first importance. The coming surveys that will map this volume more deeply are expected to find, if the interpretation is right, more individual shells. A population of named fossils, each independently measurable, would turn the oldest signal in the universe into a local, testable object, and Huge-LQG would be remembered as the first of its kind. A structure 1 billion light-years wide, hiding inside 40 years of maps, waiting for someone to connect monuments that already had names. The next structure on the countdown is even closer to home than the bubble, and in some ways it is stranger, because for all its size until the summer of 2020, not a single person on Earth knew it was there. It was hiding behind the one thing in the universe we cannot look past, our own galaxy. Number 6. The South Pole Wall. Every map of the universe we have ever drawn shares one flaw, and it is not the fault of our telescopes. We live inside a galaxy, embedded in its disk, surrounded by its stars and its dust. When we look out at the cosmos in most directions, the view is clear. But along the plane of the Milky Way itself, our sightlines plunge through thickening curtains of dust and crowded fields of stars, and the distant universe simply disappears behind them. Astronomers call this band the zone of avoidance, or more formally, the zone of galactic obscuration, and it blindfolds us across a wide swath of the sky. Whatever the universe has built in those directions, we cannot photograph it. For a century, map-makers of the cosmos have simply drawn their surveys around the blind zone and hoped nothing important was hiding inside. The 6th entry on our countdown is the demonstration of how badly that hope could fail. It is a wall of galaxies at least 1.4 billion light-years long, one of the largest structures in the nearby universe, and it lay undiscovered until July of 2020, in part because a portion of it sits exactly where we cannot see. Hundreds of thousands of galaxies, arranged into a single sweeping curtain, hidden behind the glare of home. Our phrase from the bottom of this list has followed us up the ladder. At number 10, hiding in plain sight meant clouds too faint to trust. Here, it means something enormous concealed by the dust of our own sky. It is not only the faint that hides, the enormous hides too. The structure is called the South Pole Wall, named for the region of sky where its densest portion lies, wrapped around the direction of the South Celestial Pole, the point in the heavens above Earth's southern axis. Its discovery was announced by a team of 4 cosmographers, map-makers of the universe's large-scale terrain, whose names have already threaded through this countdown. Daniel Pomerade of Paris-Saclay University in France led the work, alongside Brent Tully of the University of Hawaii, who by this point in our list needs no introduction, with Yehuda Hoffman of the Hebrew University of Jerusalem and Hélène Courtois of the University of Lyon. This is the same community of researchers who mapped the local void and who would later identify Huge-LQG, and the South Pole Wall was found with the same beautiful trick that made those discoveries possible. You cannot photograph what hides behind the Milky Way, but you can feel it. The method deserves its moment because it is one of the quiet revolutions of modern astronomy. The team worked from Cosmic Flows 3, the catalogue of 18,000 galaxy distances and motions we have already met. Each galaxy's motion is a vote, a small arrow indicating which way the surrounding mass is pulling it. No single arrow tells you much. But feed thousands of arrows into a careful mathematical reconstruction, and the hidden landscape emerges, because matter cannot hide its gravity. Galaxies on one side of the blind zone are being tugged toward something. Galaxies on the other side are being tugged toward the same something. Triangulate enough of those tugs, and you can draw the something, even though no telescope has ever seen it directly. The reconstruction reveals all the mass, including the dark matter that never shines for any telescope. The wall announced itself not by its light but by its pull, the way you might map a magnet under a table by scattering iron filings on top. And what emerged from the arrows was startling. The reconstruction showed a continuous filament of matter sweeping across the southern sky, its densest knot about 500 million light-years away, almost directly toward the south celestial pole. From that knot, the wall extends in a great arc, bending across the sky toward the north in both directions, one arm reaching toward the region of the constellation Cetus, the other toward the direction of the Norma cluster. Traced from end to end through the maps, the structure runs at least 1.4 billion light-years, a curtain of galaxies and dark matter comparable in scale to the largest structures ever charted. For comparison, the celebrated Sloan Great Wall, for years the benchmark giant of the mapped universe, is of similar length but sits roughly twice as far away. The South Pole Wall is in our neighborhood, cosmically speaking. Something half the sky wide, among the largest objects known, had been sitting on our doorstep through the entire history of astronomy, and we found it in 2020. The wall is not a straight fence. The maps show it curving, wrapping partially around our region like a windbreak around a campsite, and this shape matters for a practical reason. Mass on that scale steers its surroundings. Just as the local void pushes us from one side, the concentrations of matter in and around the South Pole Wall pull from theirs, and the motions of galaxies across an enormous volume of the local universe, our own galaxy included, are the summed result of this hidden tug-of-war. Every time astronomers measure the expansion of the universe using nearby objects, they must first account for these local currents. A wall of this size, unknown until 2020, was silently participating in every such measurement ever made before it. Our cosmic address keeps being rewritten. Within living memory, we have learned that we sit on the shore of an enormous emptiness, inside the flow lines of an enormous attractor, and now beside an enormous wall, and none of those words were on the map when the oldest astronomers alive today began their careers. But the deepest reason the South Pole Wall belongs on this list is not what has been mapped. It is what has not. Here we must let the discoverers speak for the limits of their own discovery, because they were admirably direct about it. The measured length of 1.4 billion light-years runs to the edge of the surveyed volume, not to the edge of the wall. The maps simply stop where the galaxy catalogue stops, and the structure shows no sign of ending there. Pomerede and his colleagues stated it plainly. They will not be certain of the wall's full extent, nor whether it is unusual, until the maps grow substantially larger. In other words, 1.4 billion light-years is not a measurement of the wall. It is a floor beneath the measurement, the minimum the wall can possibly be. The structure may continue on beyond the survey boundary, deeper into the blind zone, farther than the catalogue's reach, and if it does, this entry might belong several rungs higher on our ladder than the position we have cautiously assigned it. There is something almost unsettling in that, delivered calmly. We know the wall begins. We do not know where it ends. Astronomy has discovered an object whose far edge is, for now, a matter of confession rather than knowledge. The team behind the South Pole Wall had, in fact, already redrawn our cosmic address once before, and the earlier discovery explains the mindset that made the later one possible. In 2014, the same core group, Tully, Courtois, Hoffman, and Pomerede, used an earlier edition of the Galaxy Flow catalogues to answer a question that sounds almost childlike. Where does our galaxy actually belong? Galaxies gather into groups, groups into clusters, clusters into superclusters, but the boundaries of these gatherings had always been drawn loosely, by eye and convention. The team proposed a rigorous definition. Watch the flows, and draw the boundary where the currents divide, exactly as watersheds are drawn on Earth, where a drop of rain on one side of a ridge runs to one river and a drop on the other side runs to another. Applied to the universe, the definition carved the local volume into basins of gravitational drainage, and the basin that contains us turned out to be enormous, 100,000 galaxies flowing gently toward a common deep point, spanning 500 million light-years. They named it Laniakea, a Hawaiian word meaning immense heaven, and the Milky Way sits far out on one of its fringes, a suburb of a metropolis we had never named. The South Pole Wall discovery 6 years later was the same craft pointed outward, the watershed mapping extended to greater depth, and it is worth understanding that these maps are not pictures of light. They are pictures of influence, charts of where the universe's matter, seen and unseen, actually directs traffic. In such maps, dark matter appears on equal terms with bright galaxies, because the currents respond to everything. The South Pole Wall is, in this sense, one of the most complete portraits of a great structure ever drawn, mass itself, not merely the glowing fraction. The zone of avoidance, meanwhile, has its own history of humbling astronomers, and the wall is only its latest lesson. The band of hidden sky is not thin. Depending on wavelength, it blots out 10 to 20% of the heavens, and the census of what lies behind it has always run generations behind the rest of the sky. Major clusters of galaxies have been discovered lurking in it embarrassingly late, including, in the 1990s, a massive nearby cluster in the constellation Norma that plays a leading role in the flows of our whole region, and was charted only after most of the visible sky's clusters had been catalogued for decades. Radio astronomy offers one way through the curtain, since radio waves from hydrogen gas pierce the dust that blocks visible light, and dedicated surveys have slowly picked out galaxies shining through the murk in that language. Infrared surveys offer another. But the velocity method that found the South Pole Wall remains the only approach that needs no sightline at all, and its great advantage is also a small warning. It sees only what has mass enough to steer the flows. Whatever subtler things the blind zone hides, thinner walls, modest groups, the connective tissue between giants, remain unmapped, and cosmographers freely admit that the atlas of our own neighborhood is a draft with a stripe of blank pages running through it. The South Pole Wall filled in one stripe spectacularly. Nobody working in the field believes it was the last entry hiding there. Consider what that implies about the state of our maps in general. The South Pole Wall was not found in some faint frontier at the limits of telescope power. It is among the largest structures in the nearby universe, and it was hiding within 500 million light-years of home. The zone that concealed part of it still conceals whatever else lies along the plane of our galaxy, a blindfolded strip that circles the entire sky. Cosmographers estimate that a meaningful fraction of the local universe has never been directly surveyed for exactly this reason. The era of great discoveries in our own cosmic neighborhood is demonstrably not over. The wall is the proof, a monument assembled from hundreds of thousands of galaxies that every telescope on Earth technically had access to for a century, and which nobody saw until the currents of the universe gave it away. The largest nearby structures were invisible, not because they are dim, but because our own galaxy stands in the way. Our address in the universe comes with a blindfold stitched to it, and we have only begun learning to see around the edges. There is a way to make the South Pole Wall's presence feel less abstract, and it is to ask what the sky would offer if our eyes spoke the language of mass rather than light. Imagine standing outside on a clear southern hemisphere night, somewhere dark, facing toward the south celestial pole, the still point around which the southern stars wheel. To your eyes, that region offers the Southern Cross, the Magellanic Clouds, the quiet river of the Milky Way's outer bands. Now let your vision shift registers, from starlight to gravity. The familiar constellations fade, and behind them, beginning 500 million light-years out, a presence rises across the whole southern sky, a curtain of mass sweeping from horizon to horizon, curving away toward the north, on either side like the rim of an enormous bowl seen from within. It does not glitter. It looms, in the way a mountain range looms through fog, sensed as much as seen. Hundreds of thousands of galaxies stand in that curtain, most of them anonymous smudges in even our best photographs, together outweighing tens of thousands of Milky Ways. This is the actual architecture of our sky, the scenery that gravity sees, and every galaxy in our neighborhood, ours included, lives its whole history in the gravitational weather that this hidden range and its counterparts generate. Astronomers who build the flow maps sometimes describe the experience of first seeing such structures emerge from the mathematics as disorienting in exactly this way, like being handed a photograph of your own street taken in a spectrum where the largest building in the city, previously invisible, stands at the end of the block. The discipline that produces these maps has a name worth knowing: cosmography, the cartography of the universe, and its practitioners see themselves in a direct line of descent from the mapmakers of Earth's own age of exploration. The comparison is apt in one particular way. Early terrestrial maps were confident near home and fanciful at the edges, their blank spaces decorated with guesses, and they improved not by bolder guessing, but by voyages that brought back soundings. Cosmography's voyages are surveys, its soundings are galaxy distances, and its maps have improved the same way, edge by edge, decade by decade, with each new catalogue pushing the decorated guesswork farther out. The French astronomer Gérard de Vaucouleurs argued as early as the 1950s that our galaxy belonged to a larger flattened gathering he called the local supercluster, and he was treated for years as an enthusiast, overreading thin data. He was right. The structures have kept growing ever since, from his supercluster to Laniakea to the South Pole Wall, each generation's map making the previous generation's universe look like a parish chart, and there is no sign the enlargement has finished. That is the living context of this entry's open question. The wall runs off the edge of the current map, and somewhere beyond that edge, the next generation's version of this list is already waiting. The next entry was found the same patient way, by mapping rather than photographing, by treating clusters of galaxies as pins in an enormous chart. But when the astronomers who charted it added up what their new structure contained, the ladder we are climbing changed its character. Size gave way to weight. The next structure on this list is, by mass, the heaviest single thing human beings have ever identified, and when you weigh its neighborhood honestly, a quarter of all the matter in that region of the universe turns out to be gathered into just 5 colossal objects. Number 5. Quipu, the heaviest structure ever weighed. In the high Andes, long before written records arrived on the continent, the administrators of great empires kept their accounts on knotted cords. The device was called a quipu. A main cord ran through the keeper's hands, and from it hung dozens of secondary cords, each knotted at careful intervals, each knot a number, a record, a harvest, a census entry. An entire civilization's bookkeeping, stored in string. In early 2025, that ancient instrument lent its name to the most massive single structure human beings have ever identified in the universe, because when the astronomer who found it looked at his discovery, drawn out in 3 dimensions, one long principal filament with clusters of galaxies knotted along it and side branches hanging from it, he recognized the shape at once. He had seen a quipu in a museum near Santiago, Chile, during his years working at the European Southern Observatory. The name fit perfectly. The cosmic quipu is a chain of galaxy clusters roughly 1.3 to 1.4 billion light-years long, and its estimated mass is about 200 quadrillion times the mass of our Sun. If that number refuses to mean anything, here is the honest translation. Take our entire Milky Way galaxy, all of its hundreds of billions of stars, its gas, its dust, and the great envelope of dark matter that swaddles it, and call that one unit. Quipu weighs about 200,000 of those units. One structure, 200,000 galaxies worth of matter, strung on a single cosmic cord. The discovery belongs to Hans Boehringer of the Max Planck Institute for Extraterrestrial Physics near Munich, together with his colleagues, and it was published in the journal Astronomy and Astrophysics in 2025. The way it was found is a lesson in how differently the universe can look depending on which of its lights you read by. Every previous entry on this list was traced through visible galaxies or their motions. Quipu was traced through heat. The key fact is that galaxy clusters, the great gathering points of the cosmic web, are more than swarms of galaxies. The space between a cluster's galaxies is filled with gas so hot, tens of millions of degrees, that it glows not in visible light, but in X-rays. That glow is a beacon that cuts through many of the problems that plague ordinary galaxy surveys, and it marks, with high reliability, the true massive knots of the universe. Fainter groups can masquerade in visible light, but sustained X-ray glow means deep gravity, and deep gravity means genuine mass. Boehringer and his colleagues had spent years assembling a catalogue called Classics, built from the all-sky X-ray survey performed by the German Rosat satellite, a mission that mapped the X-ray heavens in the 1990s. The catalogue is, in effect, a census of the most massive objects in the nearby universe, each entry a galaxy cluster confirmed by the heat of its own trapped gas. The team then asked a simple question of their census. Within a well-defined slab of the nearby universe, at distances between roughly 425 million and 800 million light-years, how are the clusters arranged? Are they scattered evenly, the way the cosmological principle would suggest at first glance, or do they gather? They gather. The analysis revealed that the clusters in that volume organize themselves into a small number of enormous superstructures, and the greatest of them is Quipu. Its principal filament with its hanging branches contains dozens of X-ray clusters threaded like knots along the cord, and measured from end to end it runs those 1.3 to 1.4 billion light-years, making it, by its discoverer's accounting, the largest single structure currently identified in the universe, as well as the most massive ever catalogued. Notice how it compares with the previous entry. The South Pole Wall's 1.4 billion light-years came with an admission that the survey ended before the wall did. Quipu's length comes from a census of X-ray clusters with well-measured distances, which is why its discoverers were willing to call the measurement complete. Two structures, found by entirely different methods, both arriving at the same colossal scale, in overlapping regions of the nearby universe. Whatever the universe is doing at 1 billion light-years, it is not doing it only once. That is, in fact, the finding that should genuinely stop us. Quipu did not come alone. The same analysis identified 4 additional superstructures of comparable character in that single slab of sky, and together, the 5 of them account for a startling share of everything the slab contains. Roughly 45% of the galaxy clusters in that volume belong to the 5 superstructures. Roughly 30% of the galaxies do. And by the team's estimate, about 25% of all the matter in that volume, a full quarter of everything, dark matter included, is gathered into just 5 objects. Let the meaning of that settle. The textbook universe, the one described by the cosmological principle we keep returning to, is supposed to be smooth when averaged over large volumes, a fog of matter with only gentle lumps. The measured universe, in the slab where Quipu lives, keeps a quarter of its substance in 5 colossal filing cabinets. The smoothness that our equations assume does arrive eventually, at large enough scales, but the scale where it arrives keeps getting pushed outward, and structures like Quipu sit at the uncomfortable edge of what our simulations of cosmic history comfortably produce. The question the discovery quietly raises is whether our slab of the universe is typical, in which case such monsters are common and our models of structure growth need attention, or whether we happen to live near an unusual gathering, in which case our neighborhood is special, which is precisely what the cosmological principle forbids us from assuming. Either answer costs something. The satellite behind Quipu's discovery deserves its own paragraph, because the discovery is, in a sense, a message from the 1990s. Rosat, a German-built X-ray observatory whose name abbreviates the Röntgen satellite, honoring the discoverer of X-rays, launched in 1990 and spent its first half-year performing something no mission had done before, a survey of the entire sky in X-ray light. That survey became one of astronomy's enduring treasures, a complete census of the hot universe, and astronomers have been mining it ever since, decade after decade, long after the satellite itself fell silent. The Classics cluster catalogue that revealed Quipu was assembled from that survey's data, refined and cross-checked over many years, which means the raw information announcing the heaviest structure ever identified had been sitting in astronomy's archives for a generation before anyone arranged it in the way that made the structure visible. This is a quiet pattern running through our entire countdown, and worth noticing. The South Pole wall lay inside existing distance catalogues. Ho'olelana lay inside maps drawn for other purposes. Quipu lay inside a 30-year-old sky survey. The largest things in the universe are not, on the whole, discovered by new machines. They are discovered by new questions asked of old archives, which suggests, pleasantly, that more such giants may be sitting in our data right now, unrecognized, waiting for the arrangement that reveals them. There is also a scale of gathering here that rewards a moment of contemplation. A galaxy is already an extravagant thing, hundreds of billions of stars bound into one system. A cluster of galaxies is an extravagance of extravagances, hundreds or thousands of galaxies swarming in a shared gravitational well, embedded in gas so hot it outshines them all in X-rays, the whole assembly weighing as much as a quadrillion suns. Clusters are the largest objects in the universe that gravity has fully finished, collapsed, settled, and bound. Everything larger, including everything above this rung of our countdown, is unfinished business, matter arranged but not yet conquered by its own gravity. Quipu is a chain of dozens of these finished monuments, threaded by bridges of galaxies and dark matter, and that is what its mass of 200 quadrillion suns actually means. Not a smooth object but a federation, the largest gathering of finished things in the known universe, caught in the act of being loosely, temporarily, magnificently connected. When its discoverers describe the superstructure as dominating its volume of the cosmos, the domination is literal. Anything traveling through that region of the universe, light included, moves through terrain that Quipu's mass has bent. And the timing of the discovery carries its own irony. The announcement arrived in 2025, 3/4 of a century into the era of modern cosmology, from a slice of the universe that is, by the standards of this list, next door. The volume searched lies within about 800 million light-years, a region astronomers might reasonably have called well explored. Nobody expected the heaviest structure in the catalogues to be found so close to home, so late in the game, and its discoverers made exactly this point, noting that superstructures of such prominence in the nearby universe are a striking feature that cosmological models must account for. The models can produce large superstructures, and simulated universes do contain great filaments. The strain appears when one asks how often, and how massive, and how near. Each new giant found in our local volume tightens that strain by one more notch, which is the quiet, cumulative story this whole countdown has been telling. One oversized structure is a curiosity. A neighborhood containing an oversized void, an oversized bubble, an oversized wall, and the heaviest known federation of clusters, begins to look like testimony. We have now reached the midpoint of the countdown, and this is a good place to stand still for one moment and look back down the ladder, because the climb has been steep. We began at number 10 with 2 clouds of dust in our own orbital neighborhood, each 9 times wider than Earth. Structures so faint they took 57 years to confirm. At number 9, the scale leapt to a single object, 140 Milky Ways long, a pair of jets launched by one black hole. At number 8, we found an absence rather than an object, the local void, an emptiness beginning at our doorstep, so large and so hollow it shoves our entire galaxy through space. At number 7, the ladder reached the fossil bubble Ho'olelana, a billion light-years across, the frozen remains of a sound that last rang when the universe was 380,000 years old. At number 6 came a wall of hundreds of thousands of galaxies hidden behind our own sky, its far end still unmapped. And here at number 5 stands Quipu, the heaviest thing ever weighed, 200,000 Milky Ways of matter knotted on one cord. Notice what has changed along the way. In the lower rungs, the mysteries were about existence. Are the clouds real? How can the jets hold together? Why is the void so empty? From this rung upward, the mysteries change character. The remaining structures are so large that their existence itself is the problem. From here to the top of the list, every entry either strains the size limit the cosmological principle imposes or shatters it. Before we climb, Quipu has 2 more lessons, and they may be its most consequential. The first is that a structure of this mass does not merely sit in the universe. It interferes with our reading of it. The oldest light in existence, the cosmic microwave background, must pass through and around regions like Quipu on its way to our instruments, and the gravity of 200 quadrillion suns leaves marks on light. Photons crossing such a region while the universe's expansion stretches its gravitational landscape pick up slight shifts in energy, and the structure's mass can subtly lens and distort the patterns behind it. These are small effects, but modern cosmology is a science of small effects, of measurements pushed to the 4th decimal place, and Boringer's team pointed out that structures like Quipu are large enough to imprint detectable signatures on the cosmic microwave background as we observe it. The same is true of local measurements of cosmic expansion, which depend on galaxies whose motions are stirred by exactly these masses. Some of the numbers in our textbooks, the expansion rate, the composition of the universe, the age of everything, were measured through the gravity of this structure while nobody knew it was there. Quipu is not just an entry in a catalogue. It is a lens we have been unknowingly reading the universe through. There is, hidden inside this entry, a question of definition that the whole countdown has been quietly circling, and Quipu is the right place to face it. What, exactly, earns the name structure? A star is a structure by any standard, bound tight by its own gravity. So is a galaxy, and so is a cluster of galaxies, each one a finished gravitational household whose members belong to it permanently. But above the scale of clusters, the word begins to blur. Quipu is connected, its clusters linked through continuous bridges of matter, yet it is not bound, and the expansion of space will one day take it apart. The same is true of Laniakea, of the Great Walls, of nearly every giant on this list. Some astronomers therefore argue that these are not structures at all in the strict sense, merely patterns, temporary correlations in the cosmic traffic, and that the only honest giants are the bound ones. Others answer that a pattern maintained for billions of years, massive enough to bend light and steer galaxies, has earned the noun by any reasonable use of language, and that demanding permanent bondage before granting existence would strip the universe of most of its architecture. The dispute sounds philosophical, but it has teeth, because the theoretical ceiling on structure sizes depends on which definition you adopt, and some apparent conflicts between giant discoveries and the cosmological principle soften or sharpen depending on the choice. When Quipu's discoverers call it the largest structure in the universe, and others reserve that title for different objects under different definitions, both can be speaking carefully. The universe did not come with a glossary. We are writing one while standing inside the entries. The hunt that found Quipu is also, encouragingly, about to improve by an order of magnitude. A successor X-ray observatory, launched in 2019 aboard a joint German and Russian mission, has already surveyed the sky several times over, with sensitivity far beyond the old maps, and its catalogues, containing many thousands of clusters against the earlier survey's hundreds with incomparable volumes, are still being released and analyzed. Boringer's team noted the prospect directly. Deeper cluster censuses will either reveal that Quipu-class superstructures are commonplace across the universe, which would put focused pressure on the models of structure growth, or reveal that our slab of the cosmos is genuinely unusual, which would put pressure somewhere far more uncomfortable. The heaviest structure ever weighed is, in this sense, also a prediction. Within a decade, the universe will have told us whether it was a monument or a warning. The second lesson is stranger and almost poignant. Quipu is temporary. When the team examined the structure's dynamics, they concluded that it is not gravitationally bound as a single whole. Its parts are connected today, one continuous cord of matter, but the expansion of the universe is stretching the cord even as its individual knots pull themselves tighter. In the deep future, Quipu will not collapse into one titanic object. It will stretch, thin, and separate into a series of independently collapsing pieces, each cluster and clump going its own way as the space between them grows. The heaviest structure ever identified is, on the timescale of the cosmos, a passing arrangement, a formation of birds that holds its shape for one long moment of cosmic history before dissolving. We happen to be alive during the moment when the cord is whole. Astronomers of the far future, whatever form they take, will find only the scattered knots and may never know they once hung together. So the heaviest thing ever weighed is real, complete, measurable, and doomed, and its very existence leans on the boundaries of what our cosmology expects. But at least Quipu is made of the universe. It is matter, gathered by gravity, obeying the ordinary rules even while testing their limits. The next entry on the countdown offers no such comfort. It is not something astronomers found out in the universe. It is a hole that the universe may have placed around us. The next structure, if it exists, is one we are inside of right now, and its existence would mean that some of our most careful measurements of the cosmos have been distorted by our own address from the beginning. Number 4. The KBC Void, the hole we may be living in. Every measurement humanity has ever made of the universe shares a single, unavoidable feature. All of them were made from here. From one galaxy, in one place, at one time. Science works hard to erase that fact, to turn our local view into universal knowledge, and the license for doing so is the principle we keep meeting on this climb, the assumption that our location is ordinary, that the universe looks the same from everywhere, that here is nowhere special. The fourth entry on our countdown is what happens when that license comes into doubt. It is called the KBC Void, or sometimes, more bluntly, the local hole. It is a proposed region of the universe about 2 billion light-years across, in which the density of galaxies runs some 15 to 30% below the cosmic average. And the reason it outranks everything we have met so far is not only its size, though it is larger than anything below it on this list. It is the location. The Milky Way sits inside it, by most reckonings not far from its center. If the KBC Void is real, then you and every telescope ever built, and every measurement ever taken, are at the bottom of a hole 2 billion light-years wide, and some of what we call cosmic truth may simply be local weather. The name comes from three astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, whose initials it carries. In 2013, they published a study that asked one of those questions so simple it sounds almost naive. How much stuff is around us, compared with the universe's average? Their approach was patient and direct. Galaxies shine, and starlight traces matter, so counting galaxies carefully enough, across enough of the sky, deep enough into space, gives you a map of how much matter your region contains. They worked in near-infrared light, which is a deliberate and important choice. Near-infrared light comes mostly from the settled older populations of stars that make up the bulk of a galaxy's mass, and it passes through dust far more freely than visible light does. It is the most honest available tracer of where the mass actually is, least fooled by the bright froth of young stars, and least dimmed by intervening grime. Keenan, Barger, and Cowie counted galaxies in this honest light across large regions of sky, sorting them by distance, effectively asking, shell by shell, how crowded is the universe at this range, and at this range, and at this range. The answer rose to meet them like a slope in the dark. Nearby, for hundreds of millions of light-years in every direction, the counts came up short. Fewer galaxies, shell after shell, than the universe's large-scale average would predict. Only at distances approaching 1 billion light-years did the counts climb back up to normal. Their conclusion was that we live inside an enormous underdensity, a region light on matter, roughly 2 billion light-years in diameter, in which the shortfall runs perhaps 15 to 30%, depending on direction and method. And it is essential to picture this correctly, because the word void here means something different from the local void we met at number 8. That was a true hollow of the cosmic web, a region almost swept of galaxies. The KBC Void is nothing so dramatic, and in a way that makes it more unsettling. It is a shallow dish, not an empty pit. Galaxies fill it everywhere. The cosmic web runs through it. Laniakea, the enormous supercluster complex our galaxy belongs to, fits inside it whole, with room to spare. Superclusters, walls, ordinary voids, all of it continues as normal. There is simply, on average, meaningfully less of everything, sustained across a volume so large that light needs 2 billion years to cross it. You would never notice it from inside. That is rather the point. We may have been inside it for the whole history of astronomy, mistaking the bottom of a dish for level ground. Now, why is this a problem, rather than just a fact of geography? Because of the size. The standard model of cosmology does not forbid underdense regions. It demands them, and the universe is full of them. But the model makes firm statistical predictions about how deep and how large they can be, and the two properties trade off against each other. Small regions can be very empty. Enormous regions must be very nearly average, because on scales of billions of light-years, the universe is supposed to have smoothed out, with density ripples of only a few %. That is the cosmological principle, made quantitative. A whole 2 billion light-years wide and 20% deep is far outside what the standard model comfortably produces. Simulations of cosmic structure, run under standard assumptions, essentially never generate such a thing for an observer to sit in. So the stakes are stark. If the KBC Void is real, at the claimed depth and scale, then the universe is lumpier on billion light-year scales than our reigning theory allows, and the theory is missing something. Notice the shape of that argument. It is the same shape we will meet at every remaining rung of this ladder. The structure is not impossible because of what it is. It is impossible because of how big it is. Our textbook rule, the universe looking the same in every direction, is no longer merely being bent. From this entry to the top of the list, it is being broken. But with the KBC Void, uniquely on this countdown, the stakes go beyond theory and reach into the most famous open problem in modern cosmology. That problem is called the Hubble tension, and it deserves a careful minute, because if the whole is real, the whole may be causing it. The universe expands, and the rate of that expansion is called the Hubble constant. There are two great ways to measure it, and they disagree. The first way is local and direct. Astronomers use exploding stars and pulsating stars in relatively nearby galaxies as distance markers, watch how fast those galaxies recede, and read off the expansion rate. This method, refined over decades and championed by teams of formidable care, returns a value close to 73 in the units astronomers use, kilometers per second of recession for every megaparsec of distance. The second way is global and indirect. The cosmic microwave background, the afterglow of the infant universe, carries patterns whose physics is exquisitely understood. Feed those patterns into the standard model, and it predicts what the expansion rate today must be. That method returns a value close to 67. 73 against 67. The gap is small in percentage and enormous in consequence, because both measurements are now so precise that their disagreement is glaring, far beyond what the stated uncertainties permit. Cosmology has lived with this contradiction for a decade, has checked and rechecked both pipelines, and the gap will not close. Something, somewhere, is wrong, and nobody knows what. Here is what living in a giant hole would do to that story. A region lighter than average is surrounded, by definition, by regions heavier than average, and their gravity pulls outward on everything inside the hole. Galaxies within the underdensity would be accelerated toward the crowded walls, adding an extra outward drift on top of the universe's true expansion. An astronomer at the bottom of the hole, watching nearby galaxies recede a little faster than expansion alone would carry them, would innocently measure the expansion rate and get a number that runs high. Not because the universe is expanding faster, but because the neighborhood is emptying. The local measurement of 73 would then be, in part, an artifact of our address, while the global 67 would be closer to the truth. The most celebrated crisis in cosmology would be, at least partially, a misreading caused by the ground we are standing on. It is an elegant, almost embarrassing possibility. The great cosmic discrepancy, resolved not by new physics but by looking down. It is worth understanding how unusual it is for a claim like this to be testable at all, because counting the universe is an old and treacherous art. The first person to attempt it seriously was Edwin Hubble himself, in the 1930s, counting faint galaxies to ever greater depths to ask whether their numbers grew the way a uniform universe demands. The method is simple in principle and brutal in practice, because every count is filtered through the survey's limitations, how faint it can see, how well it measures distances, how much of the sky it covers, and a systematic error in any of these can masquerade perfectly as a cosmic feature. Generations of astronomers have announced local anomalies that later dissolved into instrumental subtleties, and the field carries that scar tissue consciously. What has changed in our era is redundancy. The KBC deficit has now been examined in surveys covering different wavelengths, different depths, different hemispheres, with different instruments and different teams, and this cross-checking is why the claim commands attention rather than eye-rolling. When one survey reports a shortfall, experience counsels suspicion of the survey. When many unrelated surveys report compatible shortfalls, suspicion has to be divided between the instruments and the universe, and the division is genuinely difficult. That difficulty, not any lack of effort, is why a question as basic as how much stuff surrounds us remains open in an age of precision cosmology. The depth of what rides on the answer becomes clearer when you see how the local expansion rate is actually measured, because the measurement is a masterpiece of accumulated care. Astronomers build what they call a distance ladder. The first rung is parallax, simple geometry, triangulating nearby stars against the sky as the Earth circles the Sun. The parallax rung calibrates the second rung, a class of pulsating stars called Cepheids, whose rhythm reveals their true brightness, making them lighthouses of known wattage visible in other galaxies. The Cepheid rung calibrates the third, a class of exploding stars whose peak brilliance is remarkably standardized, visible across billions of light-years. Rung by rung, distances propagate outward, until the recession speeds of far galaxies can be divided by true distances, yielding the expansion rate. Teams have spent entire careers hardening each rung, hunting systematic errors with a rigor that borders on the obsessive, and the modern local value near 73 has survived every audit. The early universe value near 67 rests on utterly different foundations. The exquisitely measured speckle pattern of the microwave background filtered through the Standard Model's physics. Two towers of evidence, each internally magnificent, disagreeing about a single number. The KBC proposal does not accuse either tower of error. It suggests instead that the local tower was built through no fault of its architects, on ground that slopes, that the ladder's far rungs stand in a region whose galaxies carry an extra outward drift, and that the two towers measure two truths, one about our region, one about the whole. It is the only resolution on offer in which everyone did their arithmetic right. One more consequence deserves mention, because it reaches beyond the expansion dispute. If the local universe truly is 15 to 20% lighter than average across 2 billion light-years, then our region's growth history differs from the cosmic mean. Structures here formed and flowed under slightly different conditions, and various local calibrations, quantities astronomy measures nearby and applies broadly, would carry small inherited biases. Some researchers have gone further and noted that a void of the claimed depth is so unlikely under standard assumptions that its confirmation might point toward modified theories of gravity, frameworks in which structure grows more aggressively than standard physics allows. That remains a minority position, and we label it as such, but it illustrates the stakes. The most conservative reading of the KBC evidence, that the counts are somehow subtly wrong everywhere, would be reassuring. The most radical reading would touch the foundations of physics. The truth is currently suspended between them, awaiting, as so much of this list awaits, deeper maps. So is the whole real? This is where the honesty this channel owes you becomes the whole story, because the evidence splits, and it splits along a fascinating line. In favor, the counts. The original near-infrared census has been joined by counts in multiple wavelengths, across multiple directions of sky, from multiple instruments, and the deficit keeps appearing, consistently, at roughly the claimed depth. Also in favor, the flows. Recent studies of what astronomers call bulk flows, the collective drift of huge volumes of galaxies measured over many hundreds of millions of light-years, report motions distinctly larger than the Standard Model predicts, and moving in patterns consistent with matter streaming outward from an emptying region toward heavier walls beyond. That is precisely the fingerprint a genuine giant void should leave on its contents. Against the reconstructions. Independent teams have built three-dimensional models of the local density field from large galaxy surveys, and those reconstructions do not clearly show a coherent whole of the required depth and size. Against the supernovae. Careful analyses of exploding stars across the relevant distances find the expansion history looking smooth, without the signature step that a deep local void should imprint as one looks from inside the hole to beyond its rim. Several of these studies conclude the local underdensity, if present at all, is too mild to generate the Hubble tension. Serious papers argue the void solves the tension. Serious papers argue the void cannot exist at the claimed scale. Both camps are competent. Both cannot be right. Step outside it for a moment, since imagination permits what physics does not. Picture yourself far beyond the region, looking back across 2 billion light-years toward home. From out here, the claimed structure would not announce itself. No edge, no darkness, just the cosmic web carrying on, wall after wall, void after void. Only by counting, patiently, region by region, would you notice the gradient, the galaxies thinning gradually toward the middle of an immense shallow basin, like lights of farmhouses thinning toward the center of a wide, dark plain. And somewhere in that thinned middle, one ordinary spiral among the sparse lights, our galaxy. On its outskirts, a small yellow star. Around that star, a planet where beings have built instruments of astonishing precision and pointed them outward, measuring the whole of everything from the one place they can never leave, the bottom of a basin whose rim, if it exists, lies 1 billion light-years beyond their sharpest maps in every direction. Every number they have ever published about the universe passed through this place on its way to being believed. There is also a psychological dimension to this entry that the purely technical account misses, and it is worth naming honestly. Of all the proposals on this list, the giant local void is the one working cosmologists seem to find most uncomfortable, and the discomfort is instructive. The other giants, whatever their fate, are at least out there, objects at safe distances, wonders or mirages in someone else's sky. This one dissolves the distinction between the measurer and the measured. Astronomy's entire method rests on the working faith that our viewpoint, corrected for known local motions, is a clean window, and the KBC proposal suggests the window itself has a curvature, gentle, invisible from inside, bending every sightline that passes through it. The unease this causes is not weakness. It is the correct response to a hypothesis that, if true, converts a decade of the field's most celebrated precision measurements into partially local statements. History, moreover, offers no comfort in the direction of dismissal. The story of cosmology across a century has been the repeated demotion of our situation from special to ordinary, each demotion resisted and each confirmed, from our position in the galaxy to our galaxy's position among billions. The KBC question is that story's strange inversion. This time, the humbling possibility is not that our place is ordinary, but that it is not, that we occupy an unusual hollow, and that the principle of ordinariness, having been right every previous time, might fail at exactly the scale where we can least afford it. That is the KBC Void. Not the largest structure on our list, but the one we may be inside, and the one whose reality would reach furthest into everything else we think we know. The resolution is coming. The newest generation of galaxy surveys is now measuring positions and distances for tens of millions of galaxies, mapping the claimed basin's full volume with a completeness the 2013 census could not approach, and within some years, the counts will simply be settled, whole or no hole. Until then, cosmology holds the strangest of its open files. The observer is part of the observation, and whether the crisis in the expansion rate is a revolution in physics or a property of our neighborhood depends on which way that file closes. Either answer rewrites a textbook, and both textbooks are currently in print. Whatever the truth of our whole, we can at least say this. Its existence is argued about politely, in percentages and statistical methods, a dispute over depth rather than shape. The next 2 entries on the countdown allow no such gentleness. We now come to a patch of sky where the universe appears to have drawn figures, deliberate-looking shapes billions of light-years across, and the astronomer who found them was a graduate student who was looking for something else entirely. Number 3, the giant arc and the big ring. The third entry on our countdown is really 2 discoveries, made 3 years apart by the same young astronomer using the same method in nearly the same patch of sky. Either one alone would have earned this position on the list. Together, They form what may be the most direct challenge yet mounted against the rule we have been testing all night. In the direction of the constellation Bootis, the northern herdsman, at a distance of more than 9 billion light-years, the universe appears to contain two enormous drawn figures. One is a curve, a smooth arc of galaxies, galaxy clusters, and gas spanning 3.3 billion light-years, a 15th of the radius of the entire observable universe. The other is a ring, a nearly circular band 1.3 billion light-years in diameter, with a circumference of about 4 billion light-years. They sit only about 12 degrees apart on the sky, roughly the span of an outstretched fist held at arm's length. Both were found by Alexia Lopez, who was, at the time of the first discovery, a doctoral student at the University of Central Lancashire in England. Remember that ceiling from the start of our climb, the theoretical limit of about 1.2 billion light-years on the size of any genuine cosmic structure. The big ring's diameter exceeds it. The giant arc is nearly 3 times larger than it. And there they both are, in one neighborhood of the sky, side by side. The way Lopez found them deserves to be told carefully, because the structures are, in a wonderful and troubling sense, invisible. At 9 billion light-years, ordinary galaxies are faint beyond the practical reach of large-scale mapping. Their starlight arrives too dim to chart a structure of this extent, galaxy by galaxy. So Lopez read the universe by a different light, one of the most ingenious tricks in the astronomer's book. She used quasars as lamps. A quasar, as we will see in richer detail one rung higher on this ladder, is the blazing core of a distant galaxy, powered by a feeding supermassive black hole, and quasars shine so ferociously that they can be seen across most of the observable universe. The Sloan Digital Sky Survey, a project that has spent more than 2 decades systematically mapping the heavens from a telescope in New Mexico, has catalogued the light of hundreds of thousands of them. And on its way to us, each quasar's light must pass through everything that lies along the line of sight, including clouds of gas far too dim to see on their own. Gas leaves fingerprints. Atoms of magnesium, drifting in the halos of galaxies and the spaces between them, absorb very specific wavelengths from any light passing through, cutting narrow, telltale notches into the quasar's spectrum. Find the notches, and you know precisely where a parcel of otherwise invisible gas hangs in space, both its direction and, from the stretching of its absorption lines by cosmic expansion, its distance. Each quasar becomes a searchlight shone through the universe's fog, and each absorption notch is a droplet of that fog, pinned to a location in 3 dimensions. Lopez was using this magnesium absorber technique to study the neighborhoods of distant quasars when the data began insisting on something she had not asked it for. Plotted across the sky, at one particular slice of distance, the absorbers, each one marking unseen gas and the faint galaxies that host it, refused to scatter randomly. They gathered into a smooth, sweeping curve, a crescent drawn across the field, coherent from end to end. She checked it, as a good scientist checks a thing she does not trust. The curve stayed. Statistical tests put the odds that random scatter would imitate such a figure at a small fraction of a percent. In June of 2021, the discovery was presented to the American Astronomical Society, and the structure was given the plain name it deserved, the giant arc. 3.3 billion light-years of correlated matter bending across the sky like a drawn bow. For scale, if the giant arc were placed in the night sky at its true angular extent, it would stretch across a span equal to 20 full moons laid in a row, all of it a single connected pattern, 10 times too large for the theoretical ceiling, drawn in gas 9 billion light-years away. Then, 3 years later, working in the same general region of sky and the same range of distances, Lopez and her colleagues, including her doctoral supervisor Roger Clowes, whose own earlier discovery occupies the next rung of our ladder, announced a second figure. This one needed no imagination to name. It is a ring, close to circular, 1.3 billion light-years across, again traced by magnesium absorbers against the light of background quasars, again coherent, again statistically robust by the team's assessment, and again enormously larger than the ceiling permits for a genuine physical structure. The Big Ring, they called it. And its geometry may be even stranger than it first appears. The team's analysis suggests the ring is probably not a flat hoop we happen to view face-on. The distribution of distances hints at a three-dimensional shape, possibly a coil, a corkscrew of matter seen down its axis so that it projects onto our sky as a circle. A drawn curve was one thing. A closed ring, or a winding coil, billions of light-years around, is quite another. Circles are shapes that dynamics has to work to produce. Nothing in the standard growth of cosmic structure, the slow gravitational gathering of matter into webs and walls, has any business producing an enormous, isolated, closed ring. It is worth being precise about why these figures are so threatening to the standard picture, because the argument is subtler than mere size. The cosmological principle allows structure. It allows quite large structure. What it requires is that, on the largest scales, structure must dissolve into statistical sameness, every sufficiently large volume of the universe resembling every other, with no privileged places and no preferred patterns. From that requirement, cosmologists have derived the rough ceiling we keep invoking, near 1.2 billion light-years, the scale by which the universe should have run out of ways to be organized. The giant arc and the big ring do not merely exceed the ceiling, they exceed it while having shapes. A slightly oversized blob could be argued away as a statistical high tide. A 3 billion light-year crescent and a closed ring are not blobs. They look, uncomfortably, like arrangements, and they sit close together, suggesting that whole region of the distant universe may be organized in a way the principle says no region should be. And this is where the phrase "we have carried up the ladder" returns with its edge sharpened. The universe is supposed to look the same in every direction. At number 8, beside the local void, that rule was being bent by an emptiness. Here, the same words carried twice the weight, because in one direction, toward Bootes, the universe appears to have left figures on its largest canvas, and no direction is supposed to contain figures at all. What could explain them, if they are real? The candidate explanations on the table are, frankly, exotic, and honesty requires labeling them as the speculations they are. One idea reaches for cosmic strings, hypothetical one-dimensional defects in the fabric of space-time, thinner than an atom yet potentially astronomically long, predicted by some theories to have formed as flaws frozen into space during the universe's first instant, the way cracks freeze into ice. A cosmic string threading the early universe could, in principle, have seeded matter along its length, and later have drawn filaments and curves of galaxies tracing its path. No cosmic string has ever been detected, and their existence remains entirely unconfirmed, but shapes like an arc are the kind of thing such a defect might leave behind. Another idea borrows from an unconventional cosmology proposed by the Nobel laureate Roger Penrose, in which the universe passes through repeating ages, and in which certain colossal events in a previous age could imprint enormous circular patterns onto the sky of the next. Ring-shaped structures have been suggested as conceivable relics of that kind. This proposal sits well outside the mainstream consensus, and we present it as exactly that, a speculative framework whose predictions most cosmologists do not accept, but the existence of an actual billion light-year ring in the sky explains why such ideas get a hearing at all. The honest summary is this. If the arc and the ring are real physical structures, then nothing in the standard toolkit builds them, and the explanations that could build them all require physics we have never confirmed. Which brings us, as it always must on this list, to the other possibility. Perhaps they are not real. The skeptical case here is serious and deserves its full weight. Human beings are pattern-finding creatures, so relentlessly tuned to see figures that we find animals in clouds and faces in wood grain, and the algorithms we write inherit our appetites. Given a large enough field of scattered points, remarkable-looking shapes will occur somewhere by chance alone, and the universe offers a very large field of scattered points. Astronomers skeptical of the arc and the ring argue precisely this, that sophisticated clustering statistics applied across enormous survey volumes are bound, occasionally, to crown a coincidence. The Discovery team has answered with their statistical defenses, multiple independent tests assigning the figures a significance that chance should not reach, and the skeptics have answered the answers, questioning how the regions were selected and how the odds were framed. This dispute is not a detail. It is the entire question, and it remains genuinely open. What can be said is that the same debate, pattern against principle, has been fought before over a different structure in this same corner of cosmology, and that structure sits one rung above us on the ladder, discovered by the very man who trained the discoverer of the arc and the ring. The choice of magnesium as the tracer is itself a small masterclass in astronomical judgment, and it explains why these particular structures could be found by a doctoral student with catalogue data rather than by a flagship telescope with dedicated time. Ionized magnesium absorbs light at a distinctive pair of closely spaced wavelengths, a double notch as recognizable in a spectrum as two adjacent missing keys on a piano. That doubling is the safeguard. A single absorption notch might be mimicked by noise or by other elements, but the magnesium pair, with its exact spacing and depth ratio, is nearly impossible to counterfeit. Better still, magnesium absorption flags gas of a temperature and density characteristic of galactic halos and their surroundings, which means each detection marks not random fog, but the gaseous environment where galaxies live. And the expansion of the universe shifts the pair's position in the spectrum by an amount that directly encodes distance, so a single quasar spectrum can yield clean, distance-tagged detections along its whole sightline. The Sloan Survey's archive holds spectra for hundreds of thousands of quasars, each a core sample drilled through the cosmos. Lopez's insight was to treat that archive as a three-dimensional excavation site, stacking tens of thousands of core samples to reconstruct the gas terrain of a single distant epoch. The giant arc and big ring emerged from that excavation, which is to say, they were found in data that had been publicly available for years. Like Quipu, like the South Pole Wall, they were not waiting for a new machine. They were waiting for a new question. It is also worth hearing how the discoverer herself has framed the stakes, because her framing is admirably careful. Lopez has described the moment of first seeing the arc as one of disbelief, followed by methodical dread, checking and rechecking, assuming an artifact, watching the artifact refuse to leave. She has also been direct about what confirmation would mean, saying that structures of this scale would call into question the assumption that underwrites the standard model of the universe, while acknowledging in the same breath that extraordinary claims face extraordinary review. Her team has presented significance estimates through multiple independent statistical methods, each assessing the chance that random scatter would produce figures so coherent, and the estimates consistently land in territory that particle physics would call discovery grade. The skeptics respond not by disputing the arithmetic, but by disputing its framing, invoking what statisticians call the look elsewhere effect. Search a large enough archive with enough freedom, they note, and somewhere in it a pattern will always pass any fixed threshold, because the number of patterns one might have found is itself astronomically large. Correcting for that effect, honestly, is one of the hardest problems in data science, and reasonable experts, applying reasonable corrections, land on opposite sides of the arc. Every giant on the upper half of our list lives inside this same methodological argument, and it is worth appreciating that the argument is not a weakness of astronomy. It is astronomy working, the immune system of a field that has been fooled by patterns before and intends not to be fooled again. There is a final scale note that belongs here, because the numbers invite one more comparison. The theoretical ceiling of 1.2 billion light-years was derived by asking when the universe's largest fluctuations should fade into statistical smoothness, and it was published with appropriate error bars, a boundary zone rather than a wall. Structures modestly beyond it, the Sloan Great Wall, for instance, could be accommodated with squinting. The upper entries of our countdown do not permit squinting. The Big Ring's diameter alone exceeds the entire ceiling. The giant arc is nearly 3 ceilings laid end to end, and both reside at a look-back of 9 billion years, an era when the universe was half its current size, meaning the structures were proportionally even more prominent in their own time, figures drawn on a smaller canvas. If they are real, they were among the most dominant features of the universe of their epoch, and the puzzle is not only how they formed, but why their era permitted them, while ours apparently does not. Cosmic history would need chapters we have not written, describing organizing forces that operated early and then withdrew. Nothing in the standard chronology behaves that way. There is one more turn of perspective worth taking before we climb. Whatever these figures turn out to be, consider what is actually at stake in the argument. The cosmological principle is not a decorative assumption. It is the license that permits cosmology to exist as a science. Only because we assume our location is ordinary can we take laws learned here and apply them to the whole. Only because we assume no direction is special can we read the universe's history from whichever patch of sky is convenient. If one region of the cosmos genuinely contains vast drawn figures that another region lacks, then that license has fine print no one has read, and some of what we have concluded about everything, from everywhere, on the assumption that anywhere is everywhere, would need to be re-examined. That is what a graduate student's absorption maps put on the table. 2 figures in the sky, and beneath them, quietly, the question of whether the universe has places. And so we arrive at the final 2 rungs. The next structure on the countdown is the one that started this entire modern argument, the discovery that first forced the phrase "too large to exist" into the scientific literature. It is a chain of 73 of the brightest objects in the universe, stretched across 4 billion light-years, and the astronomer who found it had already broken the record for the largest known structure once before, 22 years earlier. Number 2. The Huge-LQG Quasar Group. The name of the second largest structure on our list sounds like a joke, and it is not. In the formal catalogues, it is written as the Huge-LQG Quasar Group, or Huge-LQG, and the clumsiness of the name is itself a small piece of scientific history. Large quasar groups were already an established category of object, with an established name, when this one was found. The problem was that this one was so much bigger than the rest of its category that the discoverers needed a way to say so, and the word they reached for, with what one suspects was a certain dry humor, was simply huge. It is a collection of 73 quasars, arranged in a chain roughly 4 billion light-years along its longest dimension, sitting about 9 billion light-years from Earth. At the time of its announcement, in January of 2013, it was the largest single structure ever proposed in the history of astronomy. And within months of that announcement, other astronomers were publishing arguments that it does not exist. That dispute has never fully closed, and it is the reason this object earns its place so near the top of our countdown. The Huge-LQG is either the second largest thing ever found, or it is the most instructive coincidence in the sky, and the choice between those 2 readings turns out to be one of the deepest questions in cosmology. Begin with the objects the chain is made of, because they are worth a moment of respect in their own right. A quasar is what a galaxy looks like when the supermassive black hole at its center is feeding at full appetite. Gas spirals inward, compresses, and heats until it shines with an intensity that defies intuition, a single galactic core outshining the combined light of hundreds of billions of stars. Quasars are the most luminous, sustained objects in the universe, visible across nearly its entire breadth, and they are also, in the cosmic sense, brief. The feeding frenzy lasts some tens of millions of years, a flashbulb moment against the 13-billion-year age of the cosmos, and then the light dims, and the galaxy carries on in obscurity. This matters for what follows. Because quasars are so bright, they were for decades the only practical way to map the truly distant universe. And because they are so brief, each one marks not just a place, but a moment, a galaxy caught during its short blazing phase. When astronomers find quasars gathered together, they may be seeing the illuminated tips of some far larger underlying gathering of matter, most of which is dark and quiet. A group of quasars is like a scattering of lit windows across a city at night. The lit windows are few, but they imply the dark city around them. The man who found the Huge-LQG had spent his career reading the sky in exactly this way. Roger Clowes, of the University of Central Lancashire in England, was by 2013 one of the veterans of quasar cartography, and this was not his first giant. Back in 1991, Clowes and his colleague Luis Campusano had discovered a group of 34 quasars spanning roughly 2 billion light-years, the Clowes-Campusano Large Quasar Group, which stood for years as the largest known structure in the universe. A single astronomer holding the record for the biggest thing ever found is remarkable enough. Clowes would eventually be connected to the record 3 times over, because beyond his own 2 discoveries, he was the doctoral supervisor of Alexia Lopez, whose giant arc and big ring occupied the previous rung of this ladder. Whatever the final verdict on these objects, the history of finding impossible things at the edge of the universe runs substantially through one office in Lancashire. The discovery itself came from the Sloan Digital Sky Survey, the same systematic mapping project that later made Lopez's work possible. Its 7th data release included a catalogue of more than 100,000 quasars with measured positions and distances. Clowes and his colleagues ran clustering algorithms across this catalogue, mathematical procedures that ask, for each quasar, which of its neighbours lie within a chosen linking distance, then chain those connections together to find extended families. Most quasars resolve into small groups or none. But in one region, in the constellation Leo, the algorithm kept linking, and linking, and linking. 73 quasars, all at a consistent distance of about 9 billion light-years, at a cosmic epoch identified by a redshift of about 1.27, formed a single connected complex. The catalogues list it under the sober designation U1.27. Its longest axis measures close to 4 billion light-years, with a width of over 1 billion and a thickness of nearly 1 billion more, a flattened, elongated ribbon of brilliance, 3 times longer than the record holder that Clowes himself had found 2 decades earlier. Numbers this size need anchoring, so let us anchor them. Light, the fastest thing permitted, crossing this structure end to end, would depart when the Earth's oceans held nothing but single-celled life, and would arrive today. The structure is 1,600 times longer than the distance between the Milky Way and the Andromeda Galaxy. And each of its 73 beacons is a galaxy's core, burning brighter than all the stars of our sky combined. It would be, if genuine, a spine of concentrated brilliance, laid across a 25th of the observable universe's diameter, seen as it was 9 billion years ago, when the universe was not yet 5 billion years old. And there is the difficulty, arriving right on schedule. The theoretical ceiling on genuine structures, the 1.2 billion light-year limit derived from the cosmological principle, was published in its most cited form in 2010, 3 years before the announcement. The Huge-LQG is more than 3 times larger. Its announcement was the moment the polite phrase "inconsistent with homogeneity" began appearing in newspaper coverage of astronomy, and the moment the question this entire countdown keeps asking, "How large can a thing be before the universe is broken?" moved from seminar rooms into public view. The counterattack came quickly, and it was of high quality, which is exactly why this entry matters so much. Within months, the cosmologist Seshadri Nadathur published an independent statistical analysis with a sobering conclusion. The clustering algorithm that had assembled the Huge-LQG, he argued, would find similar giants in pure noise. Nadathur generated artificial skies, random distributions of points with no structure built in whatsoever, and ran equivalent linking procedures across them. Chains comparable in scale to the Huge-LQG emerged from randomness alone, not rarely but routinely. The lesson was not that anyone had erred in their arithmetic. The lesson was that connecting dots is a treacherous business, that a linking algorithm walking through a sparse catalogue will, given enough volume, assemble spectacular filaments out of sheer coincidence, exactly as human eyes assemble heroes and serpents out of unrelated stars. By this reading, the 73 quasars are real, their positions are real, but the chain is an artifact of the method, an arrangement rather than an object, with no more physical unity than a constellation. Klaus and his colleagues disputed the dismissal, defending the group's statistical distinctness, pointing to supporting evidence in the region, and noting that the same methods find the smaller quasar groups nobody doubts. The exchange ran through the literature and arrived at no verdict. A decade later, there is still none. The Huge-LQG sits in the catalogues, cited by some papers as the largest structure in the universe, and by others as a cautionary tale, both readings current, both defensible, fully 13 years after the announcement. Sit with how strange that situation is, because it is stranger than any single object could be. Astronomy possesses photographs of black hole shadows and recordings of colliding neutron stars, yet it cannot tell you whether the second largest thing on this list exists. The reason is not laziness. The reason is that the question sits at the exact boundary of what statistics can decide. Quasars are sparse, one lit window per dark city block, and at 9 billion light-years they are the only lights we can read. Deciding whether 73 of them form a genuine spine of matter or a chance figure requires knowing precisely how likely each arrangement is under randomness, and that likelihood depends on subtle choices, which volume you search, which linking distance you use, which questions you asked first, and which you asked only after seeing something remarkable. The pattern is in the data. Everyone agrees the pattern is in the data. What no one can agree on is whether the pattern is in the universe. And notice what each answer costs. Believe the pattern, and you accept a structure 3 times beyond the ceiling, with all that implies for the cosmological principle, the license behind every cosmological conclusion we own. Believe the principle, and you must explain away not only this pattern, but, somehow, the arc and the ring of the previous entry, and the accumulating family of billion light-year figures, each individually dismissible, all collectively insistent. 10 years on, astronomy still holds both answers in its hands, and has set neither down. There is one more perspective worth taking on the Huge-LQG before we leave it, and it is the view from inside. Suppose the structure is entirely real, a genuine spine of matter 4 billion light-years long, and suppose a civilization lives on a planet deep within it, orbiting some quiet star in one of the member galaxies. What would their astronomers see? The uncomfortable answer is nothing special. The 73 quasars are spread so widely that from any vantage point within the group, they would scatter across the whole sky at enormous distances, indistinguishable to the eye and to most instruments from the general population of bright cores beyond. The underlying structure would surround the observers completely and appear nowhere. Their sky would look as smooth as ours does. Only by doing exactly what clouds did, building deep catalogues, measuring distances by the 100,000, running the statistics with care, could they discover that their home was a room inside something enormous, and their first hint would arrive, as ours did, as a suspicious pattern in a table of numbers, doubted, defended, and argued over. Structures on this scale are invisible from inside by their very nature. No sky anywhere in the universe simply displays them. They exist, if they exist, only in the space between catalogues and inference, which is why the argument about them is really an argument about how much we trust inference itself, and why it cuts so deep. Nearly everything cosmology knows arrived through that same corridor. The deeper promise is that the tools sharpened on this dispute, the artificial skies, the honest accounting of search volumes, the discipline about questions asked before and after the fact, are precisely the tools now being turned on every giant we have met tonight, and on one more still ahead. Larger surveys are coming, with quasar catalogues many times richer, dense enough to test whether U-1.27 is a lit spine of the cosmic web or a beautiful accident of sparse light. The chain will either dissolve into the background, as chance figures do when the data deepens, or it will sharpen, and cosmology will have to live with what it sharpens into. Quasars themselves entered science through a mystery worth recalling, because the field's early confusion echoes the present one. When the first quasars were identified in the early 1960s, they appeared in telescopes as unremarkable points of light, star-like, hence their name, a contraction of quasi-stellar. Then, in 1963, the astronomer Martin Schmidt at Caltech examined the spectrum of a bright specimen called 3C273 and realized its light was shifted by an amount placing it billions of light-years away, which meant the unremarkable point outshone entire galaxies by 100-fold. The revelation was so disorienting that respected physicists spent years proposing alternatives, anything to avoid the required luminosities, and the debate over what quasars even were ran for a decade before the black hole picture prevailed. There is a lesson in that history for our present subject. Astronomy has faced impossible brightness before, and the resolution came not by dismissing the data, but by discovering that the universe contained an engine nobody had imagined. Whether the impossible sizes of our current era await a similar resolution, some organizing principle nobody has imagined, or await instead a statistical deflation, is exactly what the Huge-LQG dispute is about. The epoch these 73 quasars inhabit also deserves attention, because it is not a random moment. Redshift 1.27 corresponds to roughly 9 billion years ago, close to the era astronomers call cosmic noon, the age of the universe's peak productivity, when star formation and black hole feeding both ran at rates the modern universe cannot match. Galaxies collided more often, gas flowed more freely, and the great skeletons of dark matter were actively assembling their joints. If the universe ever had an era when its largest coherent gatherings of matter blazed with enough markers to be seen, cosmic noon is that era, which is part of why quasar cartographers concentrate their searches there. It is also, of course, part of the skeptical counterargument, since an era dense with beacons offers more raw material for coincidence. Both readings of the Huge-LQG agree on one thing, that we are looking at the universe's most energetic age through its brightest lamps. They disagree only about whether the lamps have been arranged. One connection deserves particular weight, and it may eventually decide the argument. The region of sky containing the Huge-LQG has been examined with the magnesium absorber technique from our previous entry, the method that reads invisible gas rather than bright beacons, and analyses have reported enhanced absorption through the structure's volume, hints of an underlying medium consistent with the quasars marking something real. The two record holders of the Lancashire School, the chain found by the supervisor and the figures found by the student, thus lean on each other methodologically, each technique offering the independent witness the other lacks. Skeptics note, fairly, that these cross-checks carry their own selection subtleties. But this is the direction from which resolution will come: multiple unrelated tracers, quasars, absorbers, and eventually the galaxies themselves, interrogated across the same volume. When the dark energy spectroscopic instrument and its successors finish their work, the quasar catalogue in that region will be many times denser than the one Clowes searched, and U-1.27 will face a jury with far more evidence than the 73 witnesses who first raised the alarm. Which brings us, at last, to the top of the ladder. Because everything on this countdown so far, the contested and the confirmed alike, has at least stayed within an order of magnitude of the ceiling. The final structure does not. The largest thing ever proposed to exist was found by accident, by researchers who were not looking for structures at all, and it is so far beyond every limit we have discussed tonight that its discoverers spent their announcement half hoping to be proven wrong. It is time to meet the wall at the top of the universe. Number 1. The Hercules-Corona Borealis Great Wall. The largest structure ever proposed in the history of science was not discovered by a telescope built to find it. It was not predicted by any theory, hunted by any survey, or imagined by any theorist in advance. It surfaced in a statistics exercise, noticed by researchers who were checking their data for something else, and when they realized what their numbers were implying, their first instinct was to look for the mistake. They have been looking for the mistake, in public, alongside the rest of the scientific community, for more than a decade now. The mistake has not been found. Neither, in the fullest sense, has the structure. This is the story of the Hercules-Corona Borealis Great Wall, a proposed assembly of matter roughly 10 billion light-years across, and it is the perfect summit for this countdown, because it gathers every theme of the night: the accidental discovery, the honest doubt, the counting of faint lights, the breaking of the ceiling, into a single object that would, if confirmed, stretch across 1/10 of the observable universe. To tell this story properly, we must begin with the messengers, because the wall was found by reading the brightest lights that exist. They are called gamma-ray bursts, and they are the most violent events the universe produces. A gamma-ray burst marks a singular catastrophe, most often the final collapse of a massive star into a black hole, or the merger of two dead stellar cores, and for a span of seconds to minutes, the eruption releases more energy than our Sun will produce across its entire 10 billion-year lifetime. For that brief moment, a single dying star can outshine the rest of the observable universe in gamma rays. Flashes this bright can be detected across almost the whole of cosmic history, from galaxies so distant and so faint that no telescope could otherwise register them. And that gives them a unique power. Every gamma-ray burst is a flare sent up from a galaxy, and galaxies live where matter gathers. Chart enough bursts, in position and in distance, and you are charting the presence of matter itself, impartially, across distances no galaxy survey can reach. The bursts do not care which galaxies are fashionable to observe or bright enough to catalogue. They fire from wherever stars die, and the sky receives them from all directions. Astronomers therefore treat them as unbiased beacons, honest sparks scattered across the depth of the universe. If the cosmological principle is true, then on the largest scales, those sparks should be scattered evenly. No direction of the sky should flare meaningfully more often than any other, once you account for how the instruments watch. Keep that expectation in mind. The instrument at the center of this story is NASA's Swift satellite, launched in 2004 precisely to catch these flares in the act, together with the worldwide network of telescopes that follows up each detection to measure a distance. By the early 2010s, The community had accumulated a precious catalogue, 283 bursts with well-measured positions and distances, each one a pin in the three-dimensional map of the universe. 283 points to describe all of observable space is a sparse map by any standard, and everyone understood that. But sparse maps can still be tested for fairness, and that is what a Hungarian and American team set out to do in 2013. István Horváth of the National University of Public Service in Budapest, Jon Hakila of the College of Charleston in South Carolina, and Zsolt Bagoli were running statistical checks on the catalogue, slicing the bursts into groups by distance and asking whether each slice spread evenly across the sky. It was methodological housekeeping, the kind of check that normally confirms everything is fine and earns a single sentence in someone's paper. Every slice passed the test except one. Among the bursts lying at redshifts between 1.6 and 2.1, corresponding to light that departed roughly 10 billion years ago, the sky was not fair. Of the 31 bursts in that distance shell, about half crowded into an area covering only 1/8 of the sky, a broad region spanning the constellations Hercules and Corona Borealis, the northern crown. Imagine tossing 31 pebbles at random across a wide floor and finding 14 of them huddled on a single tile. It happens, sometimes, by chance. The team calculated how often fairness alone would produce a huddle this tight, and the answer came out near one chance in 7,000, with subsequent analyses, depending on method, finding odds ranging from troubling to vanishing. The researchers did what careful people do. They assumed error first, reran the numbers with different statistical tools, different binnings, different assumptions, and watched the huddle survive every one of them. The clustering was in the data. In November of 2013, they published it, and the implication rang out far beyond the paper. If gamma-ray bursts trace matter, and the bursts of one cosmic era pile up in one region of sky, then that region, at that era, contains an extraordinary concentration of matter, a wall of galaxies whose extent, worked through honestly, comes out at somewhere between 7 and 10 billion light-years. 10 billion light-years. The ceiling that every previous entry on this list has strained against sits at 1.2 billion. The giant arc, at 3.3 billion, is nearly 3 times over the limit. The structure implied by the burst huddle would be nearly 10 times over it, a single coherent assembly reaching across 1/10 of everything we can see. The paper itself is a remarkable document to read, because its tone is the opposite of triumphant. The authors present the signal, present the odds, and then spend page after page arguing against themselves, cataloguing every bias they could imagine, every way the instruments or the follow-up observations might have conspired to fake a huddle. Swift does not watch the whole sky equally. Distances are only measured for bursts whose afterglows are caught in time, and telescopes on Earth favor certain skies. Could the huddle be a shadow of how humans observe, rather than of how the universe is built? They checked what could be checked, and the excess refused to dissolve into any bias they could name. And yet the discoverers declined to declare victory. Jon Hakila would say, in the years afterward, that the responsible position was skepticism of one's own result, that with only 31 bursts in the critical shell, the huddle might yet be an extraordinary accident of small numbers. The team named their candidate cautiously in the technical literature and waited for more data. The grand name it carries today was, delightfully, not their doing at all. The label Hercules-Corona Borealis Great Wall was coined by a teenager, a young Wikipedia contributor from the Philippines who wrote the structure's first encyclopedia entry and needed a title for the page. The name followed the naming conventions of earlier Great Walls. It was accurate, it was memorable, and it simply stuck, spreading from the encyclopedia into the popular press and eventually into the scientific conversation itself. The largest object ever proposed was named by a student, which may be the most honest detail in the entire story. A reminder that this discovery has belonged to the public conversation, wide open and unresolved, from its first week. The obvious question was whether more data would erase the wall, as accidents of small numbers usually are erased. The years since have delivered a slow, strange answer. It has not been erased. In 2015, with the burst catalogue grown, the team re-examined the sky and reported that the new, larger sample continued to support the clustering, and independent approaches found the same region flagged. In 2020, a further analysis published in the monthly notices of the Royal Astronomical Society revisited the question with the most reliable dataset then available, and again found the clustering present, statistically significant, stubbornly refusing to average away. A decade of accumulating data is exactly the medicine that cures statistical mirages, and this one has not been cured. Neither, however, has it been confirmed in the way structures are normally confirmed, by mapping the actual galaxies of the wall, because at 10 billion light-years, surveying ordinary galaxies across a region that size remains beyond our current instruments. We can see the flares the wall sends up. We cannot yet see the wall. So the case stands open, and it is worth stating both readings at their strongest, because this countdown owes you honesty above all at its summit. The skeptical reading goes like this. The entire edifice rests on a few dozen points of light. Small samples are treacherous in a specific, well-understood way. They permit humans to find one impressive pattern among the thousands of possible patterns nobody counted before looking. The burst catalogue grows achingly slowly, since distance measurements require quick follow-up of fading afterglows, and until the critical shell holds hundreds of bursts rather than dozens, the huddle could remain what it has always been, a coincidence preserved by insufficient data, a face in the clouds that more resolution will dissolve. The believing reading answers. The signal has survived every reanalysis, every added year of data, every methodological attack, for over a decade, which is not the usual biography of a fluke. And gamma-ray bursts are the most honest tracers we possess, blind to our catalogues and prejudices. If the huddle is real and the tracers are honest, the matter is there. But it is the third reading that earns this structure the top of our list, because suppose the believers are right. Suppose the wall stands there, 10 billion light-years of gathered matter, exactly as the flares imply. Then we face a problem far deeper than a broken ceiling, and it is a problem of time. The light of those bursts left home roughly 10 billion years ago, which means we are seeing that region as it was when the universe was between 3 and 4 billion years old. Structure grows slowly. Gravity needed most of 1 billion years just to raise the first galaxies, and the great walls of our local universe, structures 1/100th this size, required billions of years of patient assembly. For a wall spanning billions of light-years to exist that early, matter would have needed to gather across distances that, in the time available, gravity simply cannot have crossed. It is not merely that the wall is too large for the universe's rules. It is too large for the universe's history. It would be like finding a redwood forest, mature and towering, on ground that was bare rock a century before. The tools that built it, in the time available, do not exist in our inventory. Something, in that case, is missing from our account of the young universe. Some capacity for organization we have not discovered, seeded perhaps in the first instance of time, expressed in a wall we were never supposed to find with only 31 sparks. There is a rich irony buried in this story, known to everyone in the field, and it makes the wall's existence question doubly strange. Gamma-ray bursts began their scientific career as anonymous flashes with unknown distances, discovered by accident in 1967 by satellites watching for nuclear tests, and for 3 decades their origin was astronomy's loudest argument. In the 1990s, an orbiting instrument called BATSE settled the first great question by mapping thousands of bursts across the sky and finding their directions perfectly, beautifully uniform. No clustering toward the Milky Way's plane, no favored direction whatsoever. That uniformity was the decisive evidence that bursts come from cosmological distances, from the universe at large rather than from our own galaxy, and it stood for years as one of the cleanest confirmations of the cosmological principle ever obtained, isotropy demonstrated by the sky's own fireworks. The same messengers that once certified the universe's evenness are now, with distances finally attached, the messengers indicting it. Nothing about the old result was wrong. Directions alone, summed over all distances, still spread evenly. The huddle only appears when you sort the flares by depth, layer by layer, which no one could do until the afterglow revolution of the late 1990s made burst distances measurable at all. It is as if a census that once proved a nation perfectly mixed, when re-examined street by street, revealed one district of one city where a tenth of a generation had gathered. The tools improved, and the evenness developed an exception. If the wall is real, it is worth dwelling on what it would actually contain, because the phrase concentration of matter undersells it. A structure of that extent, dense enough to host an excess of dying massive stars, would encompass on the order of many millions of galaxies, with all their attendant dark matter, arranged in a connected complex wider than the distance light has traveled since the Earth formed. Its gravitational influence would organize the flows of matter across a domain thousands of times the volume of Laniakea. And we would be seeing it in its youth. 10 billion years of subsequent evolution have done something to that region, its galaxies aging, its clusters merging, its expanse stretched by cosmic expansion to even greater proportions today, and whatever it has become, its light has not reached us, and will not for billions of years. The wall, if it stands, is not only the largest object ever proposed, but the largest we will ever see this young, an ancestor portrait of a giant whose present form is beyond every horizon we own. The wall also compels a last look at the ceiling it dwarfs, because the 1.2 billion light-year limit has quietly become one of the most tested numbers in cosmology, and this list is its test. The limit is not arbitrary. It emerges from the same physics that predicts the acoustic fossils of our seventh entry, the same statistics that govern the growth of voids and walls, the same framework that passes 1,000 other checks. A single confirmed structure at 10 times that scale would not be a record. It would be a verdict, the demonstration that the universe's departures from evenness continue upward past every boundary our theory can draw, and that the hierarchy of structure, galaxy, cluster, supercluster, wall, may ascend without the summit our equations insist upon. Some cosmologists have noted the alternative reading that a universe with structure on every scale would resemble the old speculative picture of a fractal cosmos, an idea mainstream science set aside decades ago precisely because the evidence favored eventual smoothness. The evidence still favors eventual smoothness, on balance, in most analyses. But the balance is carrying more weight every decade, and the wall at the top of our list is the heaviest single stone on the scale. Picture, one last time tonight, how those sparks arrived. It is the operations center of the Swift mission, and we may compress a decade into a single imagined night shift. The room is quiet, the consoles glowing. An alert sounds. The satellite has caught a flare and has swung itself toward the source within seconds, automatic and precise. A position appears on the wall display, a point in Hercules. Telescopes across the dark side of the Earth turn, catch the afterglow, and pull a distance from its reddened light, 10 billion years deep. The point takes its place on the map. An hour passes, another alert, another point, this one far away across the sky, in a southern constellation at a different depth. The night wears on, and the map fills, point by patient point, each one the death announcement of a star that collapsed before our sun existed. And slowly, without anyone intending it, one corner of the map refuses to stay ordinary. Pins accumulate in Hercules, in Corona Borealis, at one particular depth, again and again and again over the years, while the shells above and below them stay smooth and fair. No one in the room decided this. The universe is sending its brightest flares up from one region of one era, as if something enormous there had many stars to spend. The pins do not care what they are implying. They simply refuse to spread out. The wall also invites one final act of imagination, cautious and clearly labeled as such, which is to wonder what it would be like if we could see that region as it is now, rather than as it was. The bursts that betrayed the structure departed when the universe was a third of its present age. In the 10 billion years since, if the wall is real, its galaxies have lived entire histories, generations of stars born and spent, clusters merged, quasars ignited and gone dark, and the whole assembly has ridden the expansion of space to proportions greater still. Somewhere in the universe today, on this hypothesis, the mature wall exists, the finished form of the youthful giant whose flares we are only now receiving, and nothing about it can reach us for billions of years yet. Astronomy is often described as seeing into the past, and it is, but the phrase hides its stranger twin. For structures this deep, there is a present we can never see, a current universe of finished giants whose adolescent portraits are all we will ever hold. The map we are drawing of the largest things is, necessarily, a map of ancestors. That is where the matter rests. Not settled, not dismissed, the largest candidate object in existence, hanging in the catalogues with a question mark for a foundation. The path forward is at least clear. New gamma-ray burst missions and next-generation surveys will grow the critical sample from dozens toward hundreds, and the huddle in Hercules and Corona Borealis will meet its verdict within the working lives of astronomers now young. Either the pins will finally scatter, and the greatest wall will dissolve into the most instructive coincidence astronomy has ever obsessed over, or the pins will hold their ground, sharpen, and force the question of how the infant universe built something 10 billion light-years wide. Both endings are historic. Only one of them leaves the textbooks intact. And so the ladder is complete, and it is worth one look back down from the top rung before we rest. We began tonight inside our own orbit, with 2 clouds of dust, each 9 times wider than Earth, so faint that proving they existed took 57 years of stubborn counting. We end at a wall that may span 10 billion light-years, so large that proving it exists may take another generation of counting still. Between those rungs, the same story repeated at every scale. A pattern noticed by a patient observer. A structure too faint, too hidden, or too large to be believed. An argument between the evidence and the expectation. That first cloud and this final wall differ in size by a factor so enormous that the number, roughly 1,000,000 billion times wider, communicates almost nothing, and yet they are entries on a single list, found the same way, by people who counted carefully and refused to look away from what the counting showed. And the rule we have tested all night, that the universe should look the same in every direction, has been bent by an emptiness, strained by a bubble and a wall and a chord of 200,000 galaxies, and defied outright by an arc, a ring, a chain of quasars, and a huddle of dying stars. Perhaps every one of those defiances will dissolve as the data deepens, and the principle will stand. Perhaps one of them will hold, and the universe will turn out to have places after all. You are allowed to fall asleep tonight, not knowing. So is every astronomer on Earth. The sky above your bed holds all of it at once, the dust sharing our orbit, the emptiness beside us, the fossil of the first sound, and, In one northern direction, the faint possibility of a wall across a tenth of everything. The universe has kept these questions patiently for billions of years, and it will keep them safely through this one night more. Sleep well, and good night.